right, good afternoon everybody, and thank you for joining me this afternoon. I'm glad you've decided to spend one afternoon of your weekend with me here in this seminar room. Let me start off by introducing myself. My name is Stefan Conradi and I'm the managing partner of Bayesian USA, and really glad you joined me today. So before I tell you a little bit more about myself, I was hoping that we could quickly go around the room and have everybody just say a few words about who they are so we can get a sense of our group here in our seminar. Alex, would you perhaps like to start?
Yeah, absolutely. My name is Alex Mangoff. I'm a manager, senior consultant at Burke Market Research downtown here in Cincinnati. Been working with Burke for about 8 years. Very interested in the software and kind of what the capabilities are and potentially using it in our day-to-day life. So.
Excellent. Thanks, Alex. Adnan?
My name is Adnan Sesik, and currently I'm consulting. I have my LLC company called AS Research and Analysis. But I used to work for 3 flavor companies here in Cincinnati. I used to work for Procter & Gamble, Georgia Pacific. So I was like a sensory scientist, consumer insights, and some people, they think of me as a statistician, but I'm not. So.
All right. Thank you, Adnan.
Good.
Eugene, would you like to continue?
Sure. Eugene Pedagorski. I'm a business insights manager with Zydeco. I think we subscribe now to Bayesian.
Yes, you have.
We're trying to figure out whether we can make some use of graphical modeling. So.
Okay. Thanks, Eugene. Yeah.
Hey, this is Yang. I'm working at P&G in R&D. We are using BayesiaLab to analyze consumer data.
Narayan?
Hi, my name is Narayanan. I'm also with Procter & Gamble. I'm doing similar stuff beyond. So we use this quite a bit to do reverse analysis of consumer data.
Last but not least, Austin.
My name is Austin Fry. I'm a student at Xavier University, senior, math and actuarial science. My dad works at Burke, and I interned at Zydeco last summer, so just here to learn a little bit.
Excellent. Excellent. Okay. Seems like we have a lot of common ground between everybody's background, and pretty much everybody has some link to Procter & Gamble and something. So what else would you expect here in Cincinnati? Well, let me tell you a little bit more about myself. My background is actually not in Bayesian networks. My background is mostly in the auto industry. For many years, I've worked in product management, product planning, market research, and analytics. Hey, Nick, welcome. Well, thanks for coming.
Sorry if I'm a little late.
No problem. Great to have you. In product planning, market research, market intelligence, most recently I was heading the analytics and forecasting group at Nissan North America. And over the years I've worked in many projects, or with many projects, some very successful, others not so much. And in case you're shopping for a car, I do very much recommend the Rolls-Royce Ghost. I consider that as my baby. But the reason I'm showing all these cars here is in whatever involvement I had with these projects, I was always in some form of decision support role. I was never senior enough to call the shots, but I had to prepare presentations for board meetings, etc. So everything was always about decision support, about reasoning about a problem domain. And so in many of these companies, processes were in place for supporting decisions, but often I felt they weren't particularly robust or were not grounded in science. So for many years I've been kind of exploring all kinds of statistical techniques until I came across Bayesian networks as a framework that on the one hand allowed me to model a problem domain. On the other hand, it turned out to be a framework that I could directly use for reasoning and optimization. So that was really a major insight for myself, and so I pretty much decided that I want to do Bayesian networks for the rest of my life, and I joined Bayesian. Let me now tell you a little bit about Bayesian. Bayesian actually goes back a lot further beyond my involvement in Bayesian networks. Bayesian was founded by 2 professors in the field of artificial intelligence, Dr. Lionel Shouff and Dr. Paul Monteanu. And they had originally developed this tool just for their own little research purposes. And this little tool that they designed quickly turned out to be actually quite appealing to others who wanted to use Bayesian networks for their purposes. So they decided to commercialize their tool. They called it BayesiaLab. And from these very humble beginnings, around 2001, our company has grown, and by now we have a rather respectable array of customers. Not surprisingly, Procter & Gamble remains our single largest customer, and they are, I believe, so as far as I know, employing Bayesian networks and BayesiaLab across many fields of study. But we have many market research firms, GfK, TNS, Ipsos, Kantar, Nielsen, companies in the hospitality field like Hyatt, IHG, technology firms, Intel, Microsoft. I mean, you recognize all these logos here on the screen. The point of this slide is really to highlight how universal Bayesian networks are in their application and the things you can do with them. And in our seminar today, we'll mostly focus on marketing science applications, but if you explore what all these companies are doing, it goes far, far beyond just consumer research, marketing science, etc. You have everything from military strategy to cancer research, for which Bayesian networks turn out to be a very, very helpful tool. Beyond the growth of our company, at our headquarters in France, where the company still resides in a little town near Brittany, we've expanded regionally or internationally. I am based out of our office in Nashville, Tennessee, and for some time now we've also had an office in Singapore, which is the reason why I'm traveling back and forth quite a bit. So, this seminar this afternoon is actually part of a broader program. A few months ago, we completed the seminar on marketing, mix modeling, and optimization. This was really, in a way, closely related to drivers analysis, but here it was about optimizing marketing channels, advertising channels. Today, we talk about, if you will, optimizing consumers. And pretty much with this seminar today, we conclude our chapter on marketing science. Then next month in Washington, D.C., I'll be starting with a new seminar series. And that should also be quite interesting. That's about artificial intelligence with no data. And that may sound a little bit like an oxymoron, because whenever we talk about artificial intelligence, everybody typically thinks about big data. Welcome, come on in. No problem. We think about big data and supercomputers and all those kinds of things. But as it turns out, there are actually lots of problem domains for which we have zero data. Think of new product launches. Think of any domain where there are not a lot of observations. And as it turns out, artificial intelligence can work there just as well. But that's just a quick preview, or I should say an outlook beyond today's seminar. Let me now focus on what we're going to do today. I will start off with a quick overview of analytic modeling. Sounds like a pretty ambitious task. I only want to bring some order to all these buzzwords that are floating around. Neural networks, deep learning, support vector machines, all these really cool techniques that everybody is talking about today. I want to see how all these techniques and methods relate to Bayesian networks. Now, Rihanna, I think you have a question.
Are these slides available for download?
Yes, they will. I will make all these slides available for download, along with the video that I'm recording right now. So you can relive the seminar over and over again. So from there, I will proceed to introducing the Bayesian network paradigm, which will, for many of you, will not be new, but I just want to kind of reestablish some of the fundamentals. These 2 bullet points should take roughly an hour or so, and from there we proceed to key drivers analysis. But instead of proceeding to doing it straight away, we will first run into a lot of challenges. We'll highlight a lot of problems indicating, well, how difficult it really is to perform drivers analysis, even though it sounds like such a straightforward task. So we'll probably spend about an hour just on problems. And then finally from there, we'll get into our actual exercise. We will take a data set from the auto industry and really do a soup to nuts process in building a probabilistic structural equation model that we can then use ultimately for optimization. Our objective will be to identify what we should optimize about a particular product in order to enhance overall satisfaction among consumers. And that probably should take another 1.5 to 2 hours. So, as I just mentioned a few seconds ago, all slides will be available for download. And I will also cross-reference our book because there will be many sections in today's presentation where I don't have the time to go into a lot of detail. And I will just simply say you can learn more about this topic or that topic in our book. It's available for free download from our website as a PDF. You can also get it on Amazon. But if I were you, I would probably wait until we release our next edition that is currently in the works. So let me perhaps just pass around this copy of our book so you can get a sense of what that's all about. I should also point out that as of the beginning of this year, we've started to issue microcredits for all our seminars. And you may think perhaps it's a little bit of a marketing gimmick. We've actually found that there are lots of recruiters out there who are looking for people who've either been formally trained in Bayesian networks or who've have at least some familiarity with Bayesian networks. So these are these mini credits that you can get. If you complete today's seminar, you will get such a badge which you can then post to your LinkedIn profile or share via social media, etc. Beyond today's seminar, which is, if you will, kind of a teaser, I would also like to encourage you to join one of our seminars. Our next one is coming up at in the second week of March in New York. And actually, if you want to get somebody's independent opinion on the courses that we are hosting, ask Nick in the corner there. He has gone through several of them, through the introductory course and the advanced course. You'll probably get from him a much more truthful assessment about these courses than from my pitch. But still, I'd like to encourage you to join me. We have the one that's probably coming up that's closest to you would be this course in Chicago at the end of June. Right? Do you have a question there, Ryan?
Looking at somebody who looks familiar, so I'm wondering if that person or not.
Could very well be, yeah.
Red Michael Young?
No, probably not.
Well,
Oh, okay.
I'm not sure. Okay.
all right. So, a map of analytic modeling. So that indeed sounds like a fairly ambitious task to create something like that. But I just want to get kind of some sort of organization to all these buzzwords that are floating around. And to start this process, I would like to quote a paper by Galit Shmueli titled "To Explain or to Predict." Now, I've quoted this paper for many years now. Only recently I've had the chance to meet Galit in person. She's a very, very nice lady. She's an Israeli researcher who now studies or teaches in Taiwan, rather. And in 2010, she wrote this paper and in which she highlights the challenge as it relates to distinguishing between explanatory and predictive models. She says there is a lot of researchers conflate the purpose of models. especially since nowadays it is so easy to build good predictive models, many researchers attempted, based on good statistics, good measures of fit, that well-fitting predictive models are also meaningful in an explanatory sense. And that is obviously not true. Conversely, very good, robust explanatory models may not really be the best in terms of predictive performance. And so she points it out and explains it very well. So I want to pick up on her thought and introduce an axis for model purpose. And I start here on the left-hand side with description, proceed to prediction, then explanation, simulation, and finally optimization. So in the most general sense, here on the left-hand side, we have association and correlation. On the right-hand side, we have causation as model purpose. So the next question that relates to this is, where do models come from? And traditionally, models have been built or developed based on theory. We would have encoded our knowledge, perhaps we would have hypothesized about a domain and encoded our knowledge in a regression or in some sort of functional form, and then perhaps estimated the parameters based on data. Nowadays, though, we have so much data and we have clever algorithms and fast computers that we can machine learn models from data entirely without any hypothesis, without any theory. And of course, a lot of people now think, well, perhaps we don't need theory any longer. If we just have enough data, kind of it will speak for itself. But that is absolutely not true. This is a major mistake, and we need to watch out for that. And as we go through this afternoon's presentation, I think we will see where the limitations are, how far we can take data on its own. In any case, let me now put these two axes together, model purpose on the x-axis, model source on the y-axis. And now we can perhaps take some familiar techniques and place them on this map. So I would say structural equation models and regressions, they would fall somewhere here. Clearly, they are driven by theory, and a regression or a structural equation model we can use for prediction or for explanation. Then, now the next group of techniques or methods I'm placing up there. So here we have things like decision trees, neural networks, deep learning, random forests, and there are, of course, many, many more. Now, why are they here? Well, clearly, there's virtually no theory that goes into these modeling techniques, and therefore, here that's why they are at the data end of the spectrum. And for today, I'm just covering all of these under the umbrella term machine learning. It's technically not quite correct, but I just kind of want to summarize them in terms of models that can be automatically generated from data. So that these models are coming from data is perhaps uncontroversial. But one thing we need to bear in mind is that there is one major limitation as to what these models can do, and that is all you can do with them is prediction. They are not suitable for explanation, simulation, or any other causal purpose. And I mean, just as an example, if you learn a neural network, that may be a wonderfully performing predictive device, but there is no way you can look into a neural network or a model that was built through deep learning that really you can extract anything out of it. There's nothing you can structurally interpret. It was interesting. I read an article, and I forgot where it was published, and a Mercedes researcher was interviewed about their image recognition algorithms in the context of autonomous driving. And he said, you know, our image recognition algorithms, they're now so good, they can detect things on the street, on the roadway ahead, that humans can't even recognize properly. But the challenge is, they don't know why. They don't know how, you know, this algorithm distinguishes between a tree and a pedestrian or whatever it is. It just does it. But the criteria can be extracted. So that's my point here. Well, why does this bother us that this space to the right is not covered by machine learning? Well, if we think about today's objective, we want to talk about key drivers analysis. And here I'm sharing with you a quote from a website from a British research firm. This was pretty much the first definition that popped up on Google as I was looking up what is key drivers analysis. And on that website, they say a key drivers analysis investigates the relationship between potential drivers and customer behavior, such as the likelihood of a positive recommendation, overall satisfaction, or propensity to buy a product. So I've highlighted the key term here, investigates the relationship. So this is clearly an explanatory question, which puts key drivers analysis very clearly to the right of, if you will, this wall here. So what can we do, or how could we still utilize machine learning, a non-explanatory technique, if you will, for our explanatory task? Well, as it turns out, Bayesian networks are very, very practical in this context, because we can either machine learn Bayesian networks just from data, and we will see that this afternoon. We can just discover structure from data. But we can also introduce any theoretical knowledge that we have. So this allows us to either use Bayesian networks in a non-causal way, just for predictive purposes, or we can add our causal understanding, our theoretical knowledge, and thus transform Bayesian networks into causal Bayesian networks that allow us to simulate and to optimize, or I should rather say simulate interventions in a domain, as opposed to simply performing predictive inference. But more about that later. Now, we haven't invented Bayesian networks. Rather, Bayesian networks were invented by Professor Judea Pearl. He has been teaching and researching at UCLA for, I believe, over 40 years now. And to quote him, his objective was, on the outset, to mathematize causality. So he was looking for ways to encode causal relationships, because he realized that algebra is too limited in this regard. And so he wrote his seminal papers in the mid-1980s, and since then, really Bayesian networks have really grown in popularity, but for the longest time, that popularity was confined to the field of computer science. Only more recently have researchers in other fields discovered the very, very powerful properties of Bayesian networks, and this is something we're really encouraging. It's one of the reasons why we're developing the BayesiaLab software, one of the reasons why we wrote the book. We really want to make Bayesian networks accessible and practically useful for researchers in many fields of studies. So, any questions so far? All right, I will keep moving forward, and for some of you this may be very, very repetitive if you are already working with Bayesian networks, so I'll try to be brief. A Bayesian network is a probabilistic graphical model, which means the graph is the model. There are no formulas, there are no equations. There are actually just two components. We have a node and we have an arc, and this is it. There are no other elements in a Bayesian network. And I would now like to illustrate this with an example, actually a fairly old example that was first written up by Lauritsen and Spiegelhalter in 1988. This is a story about a specialist in respiratory medicine, a lung doctor, who wants to summarize his knowledge about his patients. Look, perhaps he looks a little bit older, perhaps he's about to retire, and he wants to pass on his knowledge to his successor. So he starts off thinking about the relevant variable in this domain, and he starts off with the first variable of interest, and that is age. Now, the node age has 3 states, 1, 2, and 3, and each state has a value under 30 years of age, 30 to 65 years of age, and finally over 65 years of age. And along with the state value, we also have a probability, 25%, 40%, and 35% respectively. So it basically tells us the proportions of each age group among this doctor's patients. Now, you may ask, well, where does this knowledge come from? Well, either the doctor just happens to know that off the top of his head, or perhaps somebody went through all the patient records and counted, basically looked at each patient and recorded the age to come up with the overall age distribution. So this is our first node. Now I'm going to introduce a second node, and perhaps not surprisingly, since this is a lung doctor, whether a patient is a smoker or not will be highly relevant. So the second node is smoker, and that has just 2 states, true and false. And once again, we have the probabilities associated with the states. So not so exciting so far, but now, if you will, the magic happens because we're now introducing an arc, and that arc creates a probabilistic relationship between the states of the node age and the states of the node smoker. Here we now have a conditional probability table that links up these states. So I can now look at this table and see that given you're under the age of 30, the probability of being a smoker is 69%, and so on. So I have this table that links age and smoker. Now you'll see, well, I could probably do the same thing with a very simple Excel table. Now, it becomes more interesting when you start to add more nodes and more arcs. And here, given that he's a lung doctor, we have further lung conditions such as bronchitis, dyspnea, which is shortness of breath, tuberculosis. And here we have a node that denotes the outcome of an X-ray exam, or of a chest X-ray rather. So it could be abnormal or normal. And finally, we have a node that reflects lung cancer. Now, the way you kind of need to envision this is wherever we have a node connecting to an arc, we have these little conditional probability tables that link the states of the nodes with each other. And you may wonder, well, why do we do that? Why is this helpful? Why is this a good way of encoding our knowledge? Well, I'll now go through a whole range of properties of Bayesian networks that I think will illustrate how practical and powerful they are. Yes, Adnan?
Yeah, I apologize. Do you mind if you can go back and just again, maybe I missed the point of the probability between age and smoker.
Mm-hmm.
So how did you connect? Yeah, that part. So how did you come up with? Look like that's the key start. But
That's the start. You're absolutely right. You may ask, well, how do we know that?
right.
Yeah. So again, it could be somebody just happens to know that because somebody is very familiar with the domain, or somebody has basically looked at the joint probability table and computed this conditional probability table. Now, if we had to create this manually, it would be quite tedious. In our domain this afternoon, we will generate a structure like this and learn the parameters, learn the conditional probability tables automatically. Here, in this example, for the time being, we won't worry about, well, how exactly this was created. We'll just say the doctor created it for us. The doctor encoded his knowledge and passed it on to us. And in a minute, we will see how we can perform inference when knowledge is encoded in this way. You know? But the question of how exactly do we generate this becomes very important. You know? And we will do that. And that's where actually BayesiaLab will be extremely helpful, because we can learn structure and we can learn the tables automatically through machine learning. Yeah. So let me now go through some of the properties of Bayesian networks, and what I will do is I will try to juxtapose them with kind of a more traditional functional form, like a regression, so we can kind of see how Bayesian networks are really very, very powerful and practical for many purposes. So first of all, Bayesian networks allow you to represent all variables in a domain. Bayesian networks allow you to represent or approximate the joint probability distribution of all variables. So you don't have to make the distinction between dependent and independent variables. They are all the same. In the same way, also, numerical and categorical variables are treated identically. I do not have to distinguish between them. I don't have to transform them into dummy variables and so on. And the way we're using Bayesian networks, we use them non-parametrically. So all the knowledge is contained in these conditional probability tables. We don't have any functional forms. We don't have parameters. Yes. So comparing that to a regression, for instance, here very clearly we have independent variables and at most one dependent variable. In a Bayesian network, we don't have to make that distinction. Now, closely related to this lack of distinction is the property of omnidirectional inference, which means that as we evaluate, as we perform inference in a Bayesian network, it always happens in all directions. So I'm not confined to how I can evaluate a network. Of course, that's not the case with a regression. Here, I can set values for the x and then obtain exactly one estimate for the y. I cannot go in the opposite direction. In a Bayesian network, I could do just that. In a Bayesian network, I could set a value for y and guess estimates for the x. Yes, Eugene?
So, again, in your picture of the data, even though you define your joint distributions, I guess along the direction of the arrow, it doesn't matter, because if it wants, you're saying it can look at them both ways and it'll just,
exactly. We can
do it along the other dimension.
Even though we may specifically choose the arc direction in a certain way, we can still perform inference in the opposite direction. Yeah. Austin.
So first you want to find a conditional probability, and then you can go backwards in a way?
Well, as we build a Bayesian network, basically part of generating a network is establishing the conditional probability tables. Once we have them, we can go back and forth in all directions. Yeah. Those conditional probability tables, I will refer to them loosely as parameters, even though they are not technically parameters as in a parametric model. I like to compare Bayesian networks to a set of gears. Why is that? Well, if you think about the set of gears, it becomes apparent that you could start cranking here, and then the motion would propagate through the gears and ultimately arrive here on the right-hand side. Or I could start turning here on the right, and then the motion would propagate over to the left, and I would also see everything that happens in between. That's what we see in a Bayesian network too. So as I'm performing inference, and even though I may only be interested in this node and that node, everything in between the path, the inference path, will be entirely visible. Makes it very, very interesting for knowledge discovery, for trying to understand a problem domain. Another property of Bayesian networks, and that is that they are inherently probabilistic, which means that I can set evidence as a distribution, and I get my inference, my output, also as a distribution. Now, why is this attractive? Well, because in so many domains, if we think about sensor data, medical tests, very few observations of the world are totally certain. So evidence that we collect in the world from whatever domain it is usually has some degree of uncertainty, or actually a very large degree of uncertainty. Think about any intelligence operation where you try to gather information about a hostile situation. You know, you get hearsay, you get rumors, you pick up chatter, which is all very, very uncertain. But in a Bayesian network, I can easily combine many pieces of uncertain evidence and calculate with them correctly. So another helpful aspect here is in a Bayesian network, I can work with partial evidence, meaning if I had 100 variables, 100 nodes in a network, but I only have observations for 3 of them, I can still perform inference. Of course, there would probably be a larger degree of uncertainty than if I observed 90 or 99 of them, but I can still, with every bit of information I gain, that I enter, I can reduce my uncertainty. And this is actually very helpful if you think about the medical domain, because that's typically how a diagnostic process works. You know, you collect, you get your patient, you ask some initial questions, and then you kind of probe and collect information to reduce your uncertainty regarding the potential conditions that this patient might have. And so Bayesian networks can very nicely simulate this process, this reasoning process. But we'll hear more about this later. Of course, with a regression, I couldn't do that. A regression requires single value inputs, and all of them, because without all observations here, I won't get an estimate for my y. But if you will, all these were just side benefits, just sort of nice to haves. Now let me get to the things that really were the reason why Bayesian networks were invented. Bayesian networks can encode causal direction, whereas algebra cannot. Let me illustrate this with Newton's second law of motion. If you remember from your high school days, your physics classes, you may remember this formula: acceleration equals force divided by mass. I'm totally current on this because my 16-year-old daughter just went through this in school, so I'm totally up to speed. This formula, when we look at the way how Newton originally phrased it, he said acceleration is produced by the force divided by mass. So actually, this isn't a mere equality, but rather this is a causal assignment. A causal interpretation is possible. Now, if you take this formula and now solve for mass, now a causal interpretation is no longer possible, because at least in classical mechanics, there is no way that we can produce mass. So this is not a causal assignment, this is a mere equality. But just by looking at algebra, at the formula, we can't really tell what equal sign means what. Is it causal, is it not causal? In a Bayesian network, this is different because in a Bayesian network, we can formally assign a causal direction. And with that, we can actually allows us then to perform a number of types of inference that we couldn't do with a non-causal approach. Now, this is a little bit confusing because I say Bayesian networks can encode a causal direction, because we will also see Bayesian networks that are non-causal, where we actually don't worry about the causal direction, where we actually do not worry about causality at all, where we're just interested in representing a joint probability distribution. This is actually what we're going to do today. The Bayesian network that we will build for our main exercise this afternoon will be non-causal. But that is not to say that actually the principal reason for inventing Bayesian networks was to formally encode causality and in that context to simulate interventions in a domain. So let me now just illustrate that real quick. I will leave PowerPoint for a little while and bring up BayesiaLab. I'm bringing up this network from our doctor, and once again, I'm not yet talking about how exactly this network was created. I will now bring up two nodes. I will double-click on age and cancer. I'll make these larger. So here on the right-hand side, we have what we call monitors. These monitors in BayesiaLab allow you to essentially look inside the nodes and see what the current distribution of the values is. So for age, we already knew that. That's what the doctor directly encoded. But now here we can learn what the distribution is in terms of the presence of lung cancer.
So,
Yes, Nayara.
so this is the marginal distribution?
These are the marginal distributions, yes.
You specified all the marginals, or the data set contained.
Here, again, we don't know how the doctor encoded this. Perhaps he ran machine learning, perhaps he just happened to know.
Sure.
So, but we are just kind of on the receiving end of this network. So we'll see, okay, the marginal...
The network takes these inputs, is that fair?
Excuse me?
The Bayesian network takes the marginals as inputs.
Takes
And
these
the
inputs. Correct. So we would now learn that roughly 4% of the patients in this doctor's practice have lung cancer. Now we will use this network to perform inference. So we will now kind of query this network. We will kind of use it as an expert system. So I will set age to over 65. And in that context, I should mention that these monitors here aren't just like gauges that allow me to see what's inside the network. I can actually set observations here. I can use these to provide inputs. So I will now double-click on age greater than 65. I've set an observation here now. And given this observation, I now receive an updated probability for cancer. So now I see, given that you're over 65 years of age, then the probability of having cancer has increased to roughly 8%. So this was performing inference in the direction of the arc. But what is interesting about Bayesian networks is that I can immediately go in the opposite direction as well. So I will now set evidence on cancer. I'll say cancer equals true. And given this observation on cancer, I now get an updated distribution for age. This is now the age distribution of my cancer patients. So you may say, well, I could have done it with a simple crosstab in Excel. Why do I need Bayesian networks for that? Well, let me remove these two nodes for now and actually bring up more of these here and make that smaller. Okay, so here I have now all nodes from this network, and I will repeat what I just did. I will set evidence on age, and whereas previously we just observed cancer, we will now see how actually all the other nodes are updated too. So inference moves in all directions. In the same way, I could also replicate what we did earlier, where I set cancer to true, and all the other nodes will be updated as well. This is attractive because I'm not just limited to setting a single piece of evidence, but I can actually collect information and update all the other nodes that I have not yet observed. For instance, now I have observed cancer equals true. I'm now setting smoker equals false. And now, given these two observations, I would now learn, given that cancer is true, smoker is false, the individual or the remaining group is probably very old in age, and so on. So I can use a Bayesian network as an inference device. Let me switch back to PowerPoint.
Just before we go
Yes.
to I saw the values of standard deviation.
Mhm.
Any meanings besides I saw that they were changing from 36 units to 22 and so on. So
Yeah.
anything
No,
interesting?
these are just statistics related to the distribution that is represented in the monitors.
Okay.
Yeah. So for our purposes today, we will actually not look or not take into account these statistics, but they're just for your information, if you will. The key point I wanted to make now is really that Bayesian networks are a great inference engine. You can set the observations you know. You can enter that, if you will, dial that in, your knowledge, and turn the crank. And then the Bayesian network updates the probabilities of all other nodes in the system. Now, you may ask, well, why are Bayesian networks called Bayesian? That goes back to Reverend Thomas Bayes, who was a Presbyterian minister in the south of England in the first half of the 18th century. And he was a pastor of a small parish, but beyond that, he was also a hobby mathematician. And he was studying all kinds of things, and among his research efforts, he wrote an essay which was titled An Essay Towards Solving a Problem in the Doctrine of Chances. And in this essay, unfortunately it wasn't published during his lifetime, rather a friend of his, a certain Mr. Price, published it after Bayes' death. And this essay essentially gave to us what we now know as Bayes' rule or Bayes' theorem. That's the formula that tells us how we should update our belief in a hypothesis given new evidence. So, and that is what a Bayesian network can do. As you set observations, it updates the probabilities of all nodes in this network. So that's why Judea Pearl chose the name Bayes, or the term Bayesian network. Now, what often gets confused is because they're called Bayesian, Bayesian networks are considered to be something very, very similar to Bayesian statistics. That is actually not the case. The only reason why Bayesian networks are called Bayesian is because Bayes' rule is employed for inference. But the way Bayesian networks are generated, the way we generate them in BayesiaLab, is actually much more frequentist. So that's something to keep in mind, that Bayesian networks, despite the name, are much more closely aligned with frequentist statistics. So now, here's one more thing I'd like to point out, and that relates to Bayesian networks and artificial intelligence. Because whenever you hear about artificial intelligence in whatever context, very often Bayesian networks pop up, and you may wonder, well, where is the link? How are they a type of artificial intelligence? Well, a Bayesian network provides a knowledge base because it contains declarative and propositional knowledge. It includes associational knowledge of this and that. And finally, it also includes causal knowledge. Here, the doctor, for instance, encoded that smoking causes cancer, not the other way around. So that's, if you will, is the knowledge base, and then the network itself is the inference engine. That's our computational device. And between the knowledge base and the inference engine, we have a type of expert system. We have a type of artificial intelligence. And chances are you've used something like that already in the past. For instance, in an expert system like the WebMD symptom checker. Like when you go online, let's assume perhaps you have a cold, you enter your pieces of evidence, your observations, like you have a runny nose, a sore throat, you're coughing, you're sneezing, and so on. These would all be observations. And given that input, now the expert system would update the probabilities for all the possible conditions you could have. I recently tried it out. At the beginning of the year, I had a cold, so I entered all the typical symptoms because I was worried I might not just have a cold, but that I might have bronchitis or something like that. So I entered all the evidence, and then I got my probabilities for all the conditions. At the top, of course, there was a common cold. The next thing was bronchitis, and further down, with a much lower probability, was pneumonia, and then much further down was lung cancer. And at the very, very bottom, with a 0.01% probability, it was actually the plague. So it was not the plague, I can assure you. But that's kind of how an end user can utilize Bayesian networks. But I want to point out another angle, and that is about how you can use Bayesian networks to communicate knowledge to others. In the past, in my work at Nissan, for instance, it involved a lot of forecasting, and very often for forecasting, I would develop regression models, etc. And then I sort of went into the boardroom and presented my forecast and said, okay, here's my model. And people would say, yeah, great, Stefan, I suppose you're right, but I have no idea what all these Greek letters mean. You can't really, my audience couldn't really engage with me on this. They could at most ask, oh, what's the R squared or something like that. As opposed to when you go into a meeting with stakeholders with a graph, then you can really point to your nodes and point to the people who are domain experts and say, hey, Alex, does this make sense? This is your area of responsibility. How is that related? Eugene, you're let's say, the finance expert. How about interest rates and cash flow and so on? And so even non-statisticians can look at this graph, explore it, provide feedback, engage with it. And also once you have that feedback, once you have everybody's buy-in, then the overall result, the overall inference, whatever it is much better accepted. Yes, Eugene?
I would even add that there's a little bit of similarity between the way we talk about the Bayesian networks and decision trees.
Mm-hmm.
It's the same type of process, except this is a lot more flexible. You don't
Yes.
have to go down the chain.
Yes.
And people are a lot more receptive to those.
Yes.
People that are not coming from a background.
Absolutely, absolutely.
Anything visual.
And I think that's really critical because our models tend to become more complex, and as I said earlier, it's so easy now to build models just from data. theoretical knowledge about a problem domain is remarkably important. If you have domain experts who know how something works, you really want to get that insight. You don't want to exclusively rely on data that has been generated by some sensors. So I think Bayesian networks are really a great way to get away from black box modeling and provide a transparent expert system where really everybody can, regardless of their scientific background, can look inside and watch and see what is happening in the model. Which of course leads to the question, well, how do we get a Bayesian network? Well, that's where BayesiaLab comes in. BayesiaLab allows you to learn, to machine learn Bayesian networks from data, to edit these networks, to perform inference, to analyze, to simulate, and to optimize. So we're really emphasizing the lab part, the laboratory that BayesiaLab is, because it allows you to essentially put your entire problem domain inside BayesiaLab, and then you can go back and forth learning, testing, forecasting, validating, simulating back and forth. And because understanding, querying a problem domain usually is a very iterative process. So you can basically, the entire research process can stay within the same graphical user interface. Now, BayesiaLab is actually a suite of software tools way beyond what we're going to talk about today. Today we will just use BayesiaLab Professional, but we have APIs, we have web simulators, we have what is called the Bayesian Expert Knowledge Elicitation Environment. Lots of add-on packages that relate to your specific use case, but everything really builds on BayesiaLab as a software package that runs locally on your Mac, on your PC, on a Linux machine, etc. Yes, Eugene?
Can you briefly mention the API suite, of who the users are, etc.?
Well,
like what it's meant to
yeah.
do?
What it does is it allows you to access BayesiaLab's learning and inference algorithms programmatically.
Mm-hmm.
So here what we're doing, I will click my way through in discovering structure and simulating and so on. With the API, you could, if you have streaming data, from credit card applications, let's say, you can, on an ongoing basis, like instantly score an application based on a model.
Talking about local API versus web API.
The API you can place wherever you want it. So you place the API on your server or wherever you want to perform the learning or the inference. So it's not an API that runs on our end.
Yes.
It's all local with you.
Is that available now, the API?
Yes, it is available, yeah. So
that's like additional license?
It's an additional license, yeah. For the longest time, we've only had an inference API, but more recently, we have released a learning API, so you can continuously, automatically relearn models based on new data. Yeah. So I think what we've done is we've taken this mathematical formalism and translated into a research software, or even more, we've translated into a research workflow. So regardless of whether you have just expert knowledge or have data about your domain, or perhaps a little bit of both, with BayesiaLab, we can build a Bayesian network, and once we have this network, that's our model of the world. It allows us to perform analytics, simulation, risk management. We can facilitate a diagnostic process. We can perform optimization, and so on. We can do everything that's necessary for decision support, if you will. So, questions?
Still the API.
Oh, yes, please.
So what about the interface? Do you have a tool? Do you have a tool like program in Java or JS or Python is okay?
Java.
Java.
These are the APIs are a Java class.
Okay, thank you.
Yes. All right. I suggest we take a quick break, get a refill on coffee, and then continue in about 5 minutes. So, let's now proceed to our main topic, and I'd like to start off by introducing the data set that we will be using. We will be using a study from Strategic Vision. This study is known as the New Vehicle Experience Study, and if you've ever bought a new vehicle, chances are that you would have received this particular survey. It's very, very comprehensive. It's very widely used throughout the auto industry. And the specific data set that we have available is from 2009, so this covers model year 2009. The sample that we have available has roughly 200,000 records, and it includes over 1,000 variables. So it's a very, very, very extensive survey. And there are actually several other similar surveys that are available. And these are really the principal sources for brand and product planning in the auto industry. So when I was working at Nissan, for instance, we were always eagerly awaiting the next wave of these surveys because that would be typically your single best source of feedback on your products. So, and the reason why I'm just pointing this out is that we're not working with some dummy data or some synthetic data. We have some real data from real consumers with a lot of detail. So in that sense, I'd like to thank Strategic Vision for making this available. Now, because of the nature of this data, I can't share that with you, but we do have a public data set available that is referenced in Chapter 8 of our book. That's not on autos, that's on perfume, but with that data set that is described in Chapter 8 of our book, you can follow along precisely the same steps that I'm going to present today. Now, with this data set, we're actually just looking at a subset of all the data points that we have available. We are looking at the segment of mid-size sedans. Now, all from model year 2009, and you'll see cars like the Nissan Altima, the Toyota Camry, the Honda Accord, the Hyundai Sonata. Not a particularly exciting segment, you know, if you're into cars, but hugely important for the auto industry because the biggest volume sellers are usually from this segment, like the Toyota Camry. For many years, it has been the most sold passenger car. I'm not sure which car is currently the front runner, but for many years it was a Toyota Camry. So this is an important segment for the industry.
So what is your favorite, reasonably favorite, not the one that you started?
Oh, I'm a Mercedes man.
Okay.
So I'm very biased. I like German cars, so that would actually include Mercedes and BMW.
So the quality, you're going for the quality, right? The engine quality and car safety and comfort and so on. What about the gas man?
This, in this survey, we're basically asking, or this survey asked consumers about all attributes. Actually, we have nearly 100 attributes that are asked about in this survey. So everything from how do you like your fuel economy to emissions, to how you like your taillight design, to the sunroof, to turn signal controls, to satisfaction with body workmanship. It goes into a lot of details. Even it asks you about how satisfied you are with your spare tire. So that all is included in this survey. Actually, there are more variables even in here. I'm just looking at the 98 variables that relate to specific vehicle attributes. The survey also includes other things about, your priorities, your values, your demographics, psychographics. You can really learn a whole lot about the customer in this survey. But we're just looking at just the actual ratings of vehicle attributes. So 98 detail ratings, and then we have one rating that reflects overall satisfaction, or as it is formally called, the overall new vehicle experience. One more variable is in the set that we have, and that represents the vehicle model. So that's one categorical variable. And in total, we have roughly 4,000 responses. For all the ratings, for all variables that represent a rating, this is the scale. That's at the bottom end. 1.5 denotes very dissatisfied, and at the top end, 9.5 denotes completely satisfied. And this is the same for all the individual ratings as for the overall satisfaction. Yes?
Just curious, that scale looks somewhat unusual. The 1, 5, 7, 7.
Yes. There are probably historical reasons for how the codes kind of became what they are. That scale isn't necessarily what the consumer sees. It's basically just a 5-box scale. And it is.
So I was going to ask you, is this a 10-point scale or a 5-point scale?
These is basically the 5-point scale.
Okay.
Yeah. So in our data set, it's coded 1.5, 3.5, and so on. For the consumer, you only have these ratings.
So I believe they call it magnitude type of scale. So there's history behind it. So
Yeah. So there, how exactly why they coded it this way, I cannot say it. I have to ask the folks from Strategic Vision. But for our purposes here, I think it is irrelevant.
Okay, yeah.
So now that we have our data, we may feel confident that we can move straight to our principal task. Key drivers analysis and optimization based on consumer opinion survey data. But before we get into it, I have to say, hold on. This makes no sense whatsoever. This is total nonsense. This headline contains so many contradictions. Why is that? Well, let's look at the individual components of this title of our presentation. The first thing is driver, as in key drivers analysis. Now, driver, I would argue, is a fundamentally causal concept. I would also argue that it implies the knowledge of a causal direction. And that's in itself coherent and consistent, so there's nothing wrong there. But as soon as we mention opinion survey data, that's where everything falls apart. Because when we talk about survey data, that is very clearly non-experimental data. It's observational data only. And we know that from non-experimental data, we cannot derive any causal insights. No, causal inference is generally not possible with observational data. So here is our major conflict in the title of our presentation. Let me elaborate on this a little bit. When we have observational data, it's like we're watching data from a great distance. It has happened. We can only observe what has happened somewhere in the past in a great distance. From these observations, we can derive associations and correlations, Actually, we can build quite elaborate models that can represent joint probability distributions. We can even build very good predictive models. But what we need to realize that with observational data, all we can do is produce observational inference. And we kind of know that because all of us will probably have quoted this before: correlation does not equal causation. But we may not always follow this. Let me use the words of Judea Pearl to point out this very important distinction between observational inference or prediction and causal inference, which is the simulation of an intervention. What you see here is, if you will, a generic form of a model, y equals f of x. But what we need to realize is it really depends entirely on how we obtain the x in terms of how we can calculate this. Judea Pearl introduces these operators, the see operator and the do operator, to highlight the distinction. Because he says, if we observe evidence, if we see x, then one calculation applies, as opposed to if rather than observing a value of x, if we were to do x, as in actively setting x to an arbitrary value, then we have another calculation. This is observational inference or prediction, given that I see, as opposed to causal inference, which is given that I do. And the big problem is that this one here on the left-hand side, the model for observational inference, that is so easy to build these days because there's so many clever pieces of software. All of us can very quickly build a good predictive model on virtually any domain. But the big problem is we cannot use a predictive model as well as it may fit and use that model for causal inference. So that's the big no-no. So here we are. So here we have our first major contradiction, but we're not done yet. Let me talk about causal direction. In our study today, I would think we don't even know that. Let's think of a simple, I'm just picking out two variables here that we have from our domain. Let's look at overall satisfaction and satisfaction with price value. And this is actually a very common question. Our clients in the hotel industry, they always struggle with these variables because from data it isn't entirely clear whether satisfaction with price value causes your overall satisfaction, or whether overall satisfaction drives your satisfaction with price value. It is not clear and certainly cannot be derived from the data. If we could run an experiment, of course we can figure it out, but whenever we just run a survey or conduct a survey, we cannot do that. So perhaps you will say, well, can we perhaps just make some causal assumptions for the purposes of our study today? Well, we could. We could say, you know, here are all my 100 individual ratings, and at the center is the variable that I'm interested in, overall new vehicle experience. Couldn't I just say, for the sake of argument, all these are causes of my target node? Yes, we could do that, but that wouldn't be sufficient because we couldn't just assume that all these nodes would be independent. because there is presumably a relationship between some of these nodes. So it could be something like this, for instance. But who knows exactly what it is? We don't really know. There are actually many, many ways of how this could be configured, or what the true underlying data generating process is. So let me just stress why this is so difficult to find a true causal structure here, or even just to make an assumption. Let's think about a domain where we just have two nodes, right? Let's say N1 and N2. There are three ways how a causal structure could be created based on these two nodes. The first structure is no arc, no causal relationship whatsoever. Then the second possibility is N1 causes N2. And then finally, N2 causes N1. So two nodes, we have three possible structures. Now I'm proceeding to three nodes. Now we have 25 possible structures. So quite a bit more. And I would argue this is perhaps a little bit more difficult if we just used common sense to perhaps identify which one might be the correct causal structure of the 25. Now, if we increase that number to 100 nodes, we have a total of 1.1 times 10 to the 1600 or something possible arcs or possible networks. So and I would argue that it is completely, utterly impossible to find the correct one out of these. Just for reference, the number of atoms in the universe are estimated to be 10 to the 80th. So this is an infinitely greater number. So I'm arguing we can't make an assumption about one, or assume that one of these many, many possible networks is the correct one. So with this, I arrive at the conclusion we can't really build a causal model here. We actually need to give up on formal causal inference because we just cannot know the true causal structure. But there is one more thing why we can't do that, and that is we can't really cause anyway, because our consumers don't have dials on their foreheads on which we can dial in specific values. You know, we can't just say, oh, let's just increase our consumer satisfaction with a certain attribute and kind of like set that. That's not possible. We cannot determine our consumers' beliefs, which is totally different if we were, for instance, trying to optimize marketing spend on different marketing channels. There I have full control and can say, I spend this much on this channel, this much on online advertising, that much on TV. There I'm in direct control of these values. With the consumer, I'm not. You know, I need to come up with some mechanism that will hopefully influence my consumers' beliefs, but I can't directly cause it. If we could, I would now make you all believe that Bayesian networks and BayesiaLab is the greatest technology since sliced bread. So, but you probably believe that already anyway, so I don't need to do that. So let's just recap here the big challenge that we have with our keywords in the presentation title. So we have driver versus opinion survey data, and the last point about not being able to directly manipulate our consumers also relates to or challenges our objective of optimization. Well, what do we optimize then? You know, if we can control our consumers' minds. Additionally, we also have issues, or the issue that we actually have not a single consumer, but we have thousands or millions of possible consumers. And speaking of the challenges of optimization, well, what are my constraints for optimization? You know, why don't I just simulate that all of you rate BayesiaLab 10 out of 10? You know, why should I simulate anything lower than that? You know, what really shall I optimize here? So that's the question. But that was just our first set of challenges. These were kind of our conceptual challenges. Now we come to our statistical problems. So let's start with the first one. One of the problems that we have, and that actually applies to most surveys, is that most customers are actually quite happy with products. Here, this is for our car survey data. Actually, only 2% of all ratings across all variables are rated at below fairly well satisfied. Here are all our variables. Basically, the two lowest boxes are almost never ticked. Everybody is really quite happy. People love their cars, apparently. Actually, shouldn't really surprise us, because if you think what good of a car you can lease for $199 a month, you know, safe, economical, comfortable, you know, it's quite remarkable how good cars have become even in a bread and butter segment like mid-size cars. These are quite remarkable and would compete exceptionally well compared to high-end luxury sedans of 10 years ago, 10 or 20 years ago. So anyway, so shouldn't surprise us, but that provides a challenge to engineers and designers who now need to look at, well, what shall we improve given limited resources? What matters to consumers? What would make them happier with future products? So closely related challenges, not only is everybody rating things very highly, they're rating all attributes the same way across all 100 channels, if you will. Like if people like the controls for their turn signal, they like their sunroof, they like the appearance of their wheels, they like their spare tire. Everything is highly correlated. So if we were to plot all these individual variables and plot overall satisfaction against all these 100 individual ratings, essentially what we get is we get 100 parallel lines. Everything is like, okay, which says anything that you improve would indeed be better. You know, you improve your satisfaction with the spare tire, that's good. You improve satisfaction with fuel economy, that's great too. Everything is great. So what shall one do? Now, of course, your boss looks at this and says, you know, why don't you do like a model and look what's significant? You know, estimate parameters and then check for significance, and perhaps those are the ones we should look at. Indeed, we could estimate a regression, especially if we take the entire data set with almost 250,000 observations. We can do that, and we get actually lots of significant parameter estimates. But when we look more closely at them, so we would find that if satisfaction with warranty increases, overall satisfaction goes down. If we increase the sound system controls, if the satisfaction with sound system controls increases, overall satisfaction decreases. So we have lots of negative signs here of significant coefficient or parameter estimates. So this makes no sense whatsoever, you know, because as we saw earlier in the plot, we think if satisfaction with an individual rating goes up, then the overall rating goes up. But this shows us the opposite signs. And yet, this model actually predicts quite well. So we have a good predictive model, but it is entirely useless for interpretation, because what we have here is we have a high degree of multicollinearity, and therefore we cannot get any reasonable parameter estimates. So this is out. Regression is out. Now, your boss probably has heard about all these clever new techniques, neural networks, decision trees, random forests, and so on. Can we use one of those to kind of extract the important variables? Well, we could, and they would give us good predictive performance, but they typically would not give us any meaningful interpretability. So if we were to look at a decision tree, for instance, we could look at the structure, we could look at the hierarchy, but it wouldn't really help us understand what drives satisfaction. It would come up with a good estimate, but we couldn't use that to determine what we should improve about a vehicle. Further challenge, and this is actually a pretty big one, is survey data of this kind usually has lots of missing values. In our data set, we have roughly, it's actually a relatively small set of missing data. We only have 5% missing. But of all the survey responses we have, less than 25% are complete. So most records, most survey responses came back with at least one missing value. Now, when we look at the software that we typically use to analyze such data, there are a couple of options that typically pop up as kind of the default methods of dealing with missing values. And that's typically case-wise deletion, list-wise deletion, or means imputation. And we've all done that, we've all used that, and that's another big no-no, because these two methods are poison in any analysis, because they either change the variance of the data or they introduce a bias. So we will see how we can overcome this, or actually let me talk about it now. Bayesian networks actually help us overcome these challenges here, because they provide us a very, very intuitive, simple, and fast way of imputing missing values, because as we machine learn a Bayesian network, we can continuously re-impute the missing values as the network is being learned. Now, we could talk for quite a while just on this topic, but I'd like to refer you to our book, where we have just one chapter on missing values processing with Bayesian networks. I think it's chapter 9, if I remember correctly. So here are all the challenges now. We have this issue of fundamentally causal concept, driver, in conjunction with opinion survey data, which is inherently non-causal. Then we have the challenges related to optimization, and then finally quite a number of statistical challenges. I haven't even spelled out the dimensionality as another big issue, because we have our observations really in 100 dimensions. So what are we going to do? Well, first, as I said earlier, we will forget about causality. We will be pursuing a non-causal model. Also, our approach will involve leveraging information theoretical measures, which will make our life actually easier. By relying on information theoretic measures, we can actually very nicely machine learn a Bayesian network, and also use these measures to identify factors. So out of the many dimensions that we have, by inducing factors, we can perform a variable reduction that will make it much easier to interpret this domain. Then, in terms of optimization, I said we don't have any natural constraints, because like, why don't we just simulate everybody loves everything perfectly? But can we perhaps derive something that is more realistic, that somehow has a link to current reality? In fact, using a Bayesian network, that will become quite easy. Actually, deriving constraints will be quite natural. It'll be very easy for us to see how far we are stretching from current reality. And then finally, that's what we need to bear in mind, is ultimately we will just be simulating scenarios. We'll just say, well, what if we had this alternate reality? If our consumers were not thinking like they are today, but instead, if we could bring them to this alternate world where they would like certain things better. And our objective will be, well, what's the kind of the easiest state to get them to? Where would we like them to be? So with the least amount of effort, we can get the largest gain in overall satisfaction. So that's what we will do now. And this is the workflow I'm proposing. We're starting off with a factor analysis, and we use a machine-learned Bayesian network as a structure that will yield very, very intuitive clusters that we can use to induce factors. So we'll very easily see how kind of these factors just pop out. On that basis, we will build what we call a probabilistic structural equation model. But what we need to bear in mind that this model is actually a non-causal model. So we're abandoning any consideration of causality. And in our context, in a Bayesian network, that's perfectly fine. We can build a non-causal Bayesian network because we don't have any causal assumptions or cannot make them. And then finally, for optimization, the Bayesian network allows us to quantify the joint probability. We can immediately derive how probable or improbable a certain scenario is given what we have today. Yes, Narayan?
Why is the word structural equation model introduced? Why not just probabilistic Bayesian network?
Because what we're going to do is we're going to introduce factors that will link to manifest variables, or rather our factors will relate or will summarize underlying manifest variables. And so by introducing the layer of factors and linking up factors to our target variable, we are in fact getting a structural equation model. But we call it a probabilistic structural equation model because we don't have traditional parameters.
This is like PLS or something.
Yes,
Right?
very, very similar. You will see many, many parallels.
So basically, we are dissecting the model because of the issue. So we're taking the factor analysis.
Yes,
We're also combining two different philosophies. One is the structural equation model approach, another one is the probabilistic approach.
Yes, we're kind of merging all that. We're bringing together, if you will, the best of all worlds, and for our objective here.
And speaking of that, how this, I mean, I know that there's difference, but how this would be SPSS Amos?
Yes, it would be. Yeah, that would be kind of a parallel approach.
Parallel approach.
Yeah,
okay.
yeah. So, let me just say a few more words about some of the advantages, because you may now say, why don't we just do a traditional structural equation model? Forget Bayesian networks. Why don't we do it with Amos, for instance? Yeah? Well, as it turns out, through machine learning, we can actually very nicely discover relationships among variables that would be much more difficult to detect compared to a traditional factor analysis. In the Bayesian network also, we have the ability, what we call, to embrace collinearity. So whereas traditionally you find collinearity to be a nuisance, a problem in your modeling, in a Bayesian network, it's just part of what your reality is. If nature has collinearity, then the model should have collinearity too. And then, of course, without having any parametric constraints, any nonlinearity that we may have in our underlying domain is not a problem. No? Chances are that some of the relationships that exist in the underlying domain, that they are nonlinear. With a Bayesian network, we don't have to worry about it. Whatever that relationship is, we can learn it. And then finally, I already mentioned it a few seconds ago, in the Bayesian network, we can very easily handle missing values. So now looking at our map from earlier, what we're now bringing together is the benefits of machine learning, or benefits of machine learning a Bayesian network, and then extending this into our explanatory space and use the Bayesian network for key drivers analysis. So that's what we're now going to do. A few things about nomenclature, because now it may easily get a little bit confusing, because I will be talking about factors as opposed to manifest variables. And so far I haven't spoken of manifest variables because all nodes, all variables that we only had variables that we actually observed. Now we have manifest variables that were actually observed, as opposed to factors or latent variables that are theoretical constructs. We're now essentially making up new variables that are theoretical constructs that are supposed to represent underlying manifest variables. So, and here, just cross-reference to other techniques, these factors we could, of course, also generate through, let's say, a principal components analysis. What we will see here, through learning a Bayesian network, it will actually become a lot easier. Yes, Eugene?
And so it's conceptually similar to that, except your latent factors don't have to be, linear sum.
Yes. So, yeah.
That's neat.
So, we're actually going to use some information theoretic measures, and some of you may have been exposed to these concepts in like computer scientists or electrical engineers are typically quite familiar with these. And a lot of this goes back to the groundbreaking work by Claude Shannon in the 1940s and 1950s. The first concept I'm going to introduce is entropy, which is a measure of uncertainty, and closely related to that, mutual information. And then finally, arc force, which I'll just mention briefly here, but which will play an important role in defining factors. To read more about these concepts, take a look at Chapter 5. There we have spelled them out in quite a bit more detail, but I will explain them in a minute. So here are all our 100 variables with their corresponding distributions. I first want to introduce now entropy as a measure of uncertainty. And I'll start off my example by looking at a case where we have no uncertainty. I will look at our variable or our node overall new vehicle experience, and if that variable took on the state greater than 9, then this variable would be known with certainty, in which case the entropy would be minimal, would be 0, because we know the state of this particular variable with perfect certainty. It's like when we roll a die and it lands, we see exactly what the value is. Before we roll it, however, we have complete uncertainty. So we don't, here, if we had complete uncertainty regarding our variable overall new vehicle experience, that would be the case if all states had equal probability. Now, if everything were equally possible, if we had a uniform distribution regarding all the states of our node, of our variable, then we would have the maximum entropy. So in this case, if we calculate the maximum, if we calculate the entropy, here it would have a value of 2 as opposed to 0 in the case of no uncertainty. So these are the two extreme cases. Now we can actually compute the uncertainty, we can compute the entropy for any distribution. So here, as an example, I'm showing the marginal distribution for overall new vehicle experience. And we can compute the value for this distribution with this famous formula with H representing entropy. X is our distribution of the variable. And then the formula is minus P log P, where P represents the probability of a state X. So it sums up it basically sums up P log P of each of these individual states. And with that, we can compute the marginal entropy. So as opposed, here we have 0, no entropy. 2 is our maximal entropy. And for this marginal distribution, it turns out to be a value of 1.54. So you may wonder, well, what is this good for? Well, it becomes much more interesting when we now look at this entropy in the context of other variables. So here, I'm now introducing a second variable reflecting safety features, the consumer's satisfaction with safety features. I'm just arbitrarily picking one of the 100 possible variables. What I will now do is I will look at these two variables together and first set safety features to the lowest state and observe the corresponding distribution with overall new vehicle experience. I'm basically now setting evidence and performing inference like we did in the expert system earlier. I'm just arbitrarily setting safety features to the lowest state. I get a conditional distribution for overall new vehicle experience, of which I can compute the entropy. So I'm now going through each possible state for safety features, and each time computing the conditional distribution, and each time also computing the entropy. So now I can compute a conditional entropy, or I can compute the entropy of overall new vehicle experience conditional on observing safety features. Yeah? So why do we do that? And now it becomes interesting. Let me draw your attention to this term here. This is what we just computed here. I'm computing the entropy of overall new vehicle experience given observing the safety features. This is what we did here. What we did on the previous slide was computing the marginal entropy of overall new vehicle experience. And now this is interesting. This is what we're looking for. We're now, if we subtract conditional entropy of overall new vehicle experience from the marginal entropy, we get what we know as mutual information. So this is the measure that will be very, very important for our purposes, because it tells us how the knowledge of another variable reduces our uncertainty regarding the variable of interest. So this now tells us, if we know the value of safety features, if we know this variable, then our uncertainty, our entropy regarding overall new vehicle experience is reduced by 2.48. That is our mutual information. And this is actually a very clever measure, because it applies regardless of what the relationship is. Because here, I don't even know how exactly they're related, whether it's linear or nonlinear. You know, there could be any kind of crazy curve that links these two variables. It doesn't matter. If there is mutual information, if there is common information between them, mutual information captures that. So that makes it very attractive. You could, if these variables were linearly related, then it's pretty much the same as correlation. But without knowing what that relationship is, mutual information can capture this very important characteristic. Yes, Narayana.
Correlation or partial correlation? Partial.
Well, here in this case, if we just look at two, it would just be correlation. Yeah. So let's just take a quick look at what we could do with this. We will actually often use mutual information as a measure of importance. Because if we could think of a variable that can reduce my uncertainty regarding another variable, a very intuitive interpretation is, well, then the one variable is quite important with regard to the other variable. So I'm now plotting all my 100 variables here, and on the x-axis I have the rating. This is what the consumers have, how the consumers have rated all these variables. And then on the y-axis I'm plotting mutual information, and I interpret that as importance. And now we can just take a look at some of these variables here. And let's start here in the bottom left-hand corner here. Here, for instance, we have spare tire. It appears to be that consumers on average rate spare tire as rather poorly. But on the other hand, it appears to not matter much with regard to their overall satisfaction. Shouldn't surprise us. Most people probably have never seen their spare tire. Yeah? So let's look at something that might be quite important with regard to overall new vehicle experience. And that is, for instance, the variable length of time vehicle will remain solid, durable. So that's apparently very important. And here rated higher in spare tire, but still below average of all the ratings. We can now actually go through all these quadrants, and there is sort of a nice, easy interpretation here. For instance, here the ones here in the bottom left, you know, people don't like, are not particularly satisfied, but it doesn't matter. Here, the ones here, people are not satisfied, but these are highly important variables. So these are the variables that represent unmet needs. So this is perhaps the area where somebody should invest and figure out how to improve satisfaction. Over here to the right, that may be keep up the good work, you know, highly rated and important, so this is good. So keep doing this, as opposed to down here, where things are highly rated, but not really important. There you risk running into overkill. You know, it's like you do something, but nobody really appreciates it. So, just as a quick side note, what I find interesting is where fuel economy sits on this graph. Bear in mind that this survey was done in 2009 at the peak of the recession. So, even though people were not particularly happy about the fuel economy, apparently it didn't have much importance or much relevance with regard to their overall satisfaction. That I find just rather curious. Yes?
Where is this survey taken?
It was in the US, yeah. So this was really at the peak of the recession. Yeah.
This is for Nissan,
No, this is all products.
all products.
Well, all mid-sized products.
Mid-size products, okay.
So, but the picture looks virtually identical if you do this on all 200,000 surveys across all segments.
So Stefan, the y-axis is bivariate mutual information.
Yes. Mhm.
Each variable separately.
Yes. So this would just be the bivariate mutual information between fuel economy mileage versus overall new vehicle experience. So,
How the survey, okay, well, maybe this is not the topic, but how the survey is basically built and questionnaire collected. So I just saw briefly the questionnaire, so the ballot up front. So is there anything that is missing? How the questions were collected, and so what was the method?
yes. So I'm not going into any details about, were there any conceptual issues with
Right.
this survey. I'm just taking the data set
The
from
data.
from the survey, and it is not my role to,
Yeah.
second guess their method. What I should say is that they've been working or they've been conducting this survey for several decades now.
Yeah,
So it is, in fact, has become the reference standard in the industry,
Sure.
which also makes it a little bit difficult to kind of change it and update it because you're looking for consistency so you can compare year over year, how your brand or your product has improved and so
Yeah.
on.
The thing is, if it's a standard, for example, the cars in 90s, from 90s and now, they look different with the same surveys. So
Yeah. So there are certainly, over the years, they've had to add new questions.
Right.
Questions about telematics, now functions related to autonomous driving. Those are features that didn't exist just a few years
Yeah.
ago. So, but there's a core set of questions that just has remained in the survey, which makes it really very interesting to observe it across decades.
Right.
And then also it was very interesting to watch the survey before and after the recession and what has changed, or rather what has not changed. Because actually preferences of consumers have remained remarkably unchanged as a result of the recession. So the people's perception of vehicles, what they like, what they dislike, has pretty much not changed. Yeah.
Two questions.
Yes.
Stefan. Is this the result of a multi-quadrant plot in BayesiaLab?
No, this is just plotting we will do a multi-quadrant plot in a little bit.
Okay.
It will be part of our workflow now.
So this is not a BayesiaLab output?
It is a BayesiaLab output, but it's just kind of FYI. It is just an illustration of how we can interpret mutual information.
The other question is, if I were to plot simple correlation, bivariate correlation on the y, and average on the x, how different would that plot be?
If all the relationships were perfectly linear, then it would be the same. If there is any nonlinearity in your relationships, then it would be different.
So this is the mutual information, which is the reduction in uncertainty,
Yes, exactly. Yes.
considered, interpreted as importance.
Yes, that's what we do. Yeah. So, here is the workflow that I'm now proposing. We will start off by machine learning a Bayesian network. We will validate this network. We'll perform some testing. On that basis, we will perform clustering. We will actually see how the clusters literally pop out from the network. We will review those clusters to see whether that is consistent with our domain understanding, whether these clusters make any sense. And on that basis, we will then formally generate factors and introduce new variables into the network. That serves then as the basis for building our probabilistic structural equation model. And then we can proceed to multi-quadrant analysis, what Narayan just mentioned. Can then see the importance of variables specific for each separate vehicle model. Because as we start this, we will build a new model on the entire data set or on all vehicles in the segment of mid-size sedans. But then we will want to see how do they differ between different vehicles. So, and then finally, this will be our objective. We want to optimize. We will want to see, well, what scenarios would represent our low-hanging fruit. How can we most easily improve the perception of our consumers with regard to our product? So, now for learning a network, we actually have the very same problem that we had earlier, because the BayesiaLab has the same number of possible networks available that we would have had to think about. BayesiaLab has this enormously large search space. Now, given the size, we can't possibly try out all networks. Because you would say, well, why don't we just test all of them and see which perhaps fits the best? Well, with this enormously large number, that is not possible. So, BayesiaLab uses a heuristic search, and the search metric is what we call, or what is known as the minimum description length. So BayesiaLab is trying out different networks, trying to improve this minimum description length score. That score actually represents two individual measures. One, reflecting the complexity of the network. That's the decision length of the Bayesian network, essentially the number of arcs. And the second component of the score relates to fit. That is the description length of the data given the Bayesian network. So as BayesiaLab tries out many different networks, it keeps looking for, well, what is the minimum description length score for each instance, and then is trying to reduce that score. And then finally it arrives at kind of the best possible network. We actually have the ability to influence this a little bit. We could put our thumbs on the scale through this coefficient, the structural coefficient alpha. That would allow us to say we're okay with, it would basically allow us to change the penalty for complexity. So we can either increase or decrease that given special considerations. For our purposes here, we're not going to worry about the structural coefficient. So, let me now leave PowerPoint for quite a while. Yes?
Before you go there, so for this minimum description length, we are using heuristic search method to find the
Yes.
hopefully global
Yes.
minimum. And then you mentioned earlier the missing value, right?
Mm-hmm.
If you have a missing value, say large portion, two extremes, say 90% of the value are missing, theoretically you're gonna hit a lot of multiple minimum, right?
Mm-hmm.
If we're using heuristic search, it will, like in this extreme case, 90% of the value are missing. We are almost guaranteed to hit a local optimum. Do you have like a cutoff missing value percentage?
Yes. No, there is no fixed threshold in terms of what the maximum amount of missing values is. Now, the approach that BayesiaLab takes for working with missing values or searching for missing values is at each iteration, the missing values are re-estimated. So initially, with an unconnected network, BayesiaLab would temporarily perform a means imputation. Yeah? Then learns the first network, and then updates all the missing values conditional on the network structure.
Yeah.
Then learns again, and learns again.
That's
and
like a EM.
Yes,
time.
this is the expectation maximization. But you're absolutely right. There is always the risk that you're stuck on a local minimum. And by using different search strategies, the analyst has to make sure that we're not stuck on a local minimum. The sad truth is, given the enormously large search space, we can never be absolutely certain that we have truly found the global minimum. We can just, through different methods, through different search strategies and methods like ARC cross-validation, data perturbation, reduce our chances that we're on a local minimum. We will actually use one of these techniques to help prevent that.
So we don't have even empirical cutoff value on
No,
percentage of missing.
No, we don't. So let me leave PowerPoint. Go back to BayesiaLab. And I will skip the process of importing data because it's not particularly interesting. And you can easily read up on that in the book about the individual steps. I'm now loading the data set basically as if we had just fully completed the data import process. So what we see are 100 variables now. You can count them if you wish. You can also get a little count, a variable count here in the bottom right-hand corner. Of these 100 variables, or 100 nodes, 98 are individual ratings. I'm just zooming in here a little bit so you can see what they are. You know, it really goes into a lot of detail. Rear visibility, door handles, interior lighting, turning radius, body workmanship, you know, all kinds of things. Now, there are two variables that I will initially exclude, and that is the variable, the node for model and for overall new vehicle experience. Those we will bring back later.
What does model represent?
Model, the vehicle model.
Oh, okay.
So
It's a categorical variable.
categorical variable, Altima, Camry, Accord, Hyundai Sonata, and so on. So, for now, we obviously don't have a Bayesian network. That is our next step. We now want to apply a machine learning algorithm to produce our first network. Now, we have quite a number of options for learning. And I should mention that there are two major classes of learning algorithm. One is the class of supervised learning algorithms, highlighted here. And there are actually numerous algorithms within this class of algorithms. Those we would use if we just wanted to build a predictive model, for instance. If we just wanted to, let's say, predict a specific score as a function of all the other variables. We, at this point, want to use unsupervised structural learning. We want to initially build just a model that includes all variables that we have. And within this class of unsupervised structural learning algorithms, we again have quite a choice. We're going to use the simplest and the fastest one. It's actually a highly constrained search algorithm. I'm using that simply so we can proceed quickly in our demo here today. If we were to do this for real, I would probably go through a sequence of different learning algorithms to make really sure I have the best possible network. So I will choose the maximum weight spanning tree. Let me start that. And before I could finish my sentence, it's already done. This is now my first network. As it is displayed here, it's not particularly attractive because all the lines are crisscrossing, all the arcs are crossing. So I will use our layout algorithm, our automatic layout algorithm, to untangle this mess. And now we can simply zoom in and look what do we have, what do we see. Perhaps I will zoom into this particular area. So what do we see here? Here is a node: freedom from wind noise, freedom from road noise, freedom from engine noise, freedom from rattles and squeaks, smoothness of transition, and smoothness at idle. Seems like, okay, these are conceptually closely related. They appear to be all in one branch here. What do we have here? Defrost, defog, HVAC vents, operation of HVAC controls, wiper system controls, window controls, speed control system. Okay, these are, could argue, closely related. What do we have here? Front seat roominess, second row seat roominess, ease of front seat entry, ease of second row seat entry, passenger seating capacity, going this way, interior storage space, cargo capacity, down this direction, supportive seats, front seat comfort, and so on. You can see, okay, these are, it's kind of plausible, so there seems to be a natural clustering immediately emerging. But you may now say, well, how are we sure that this is actually the best possible network? Actually, we're not sure. Therefore, we should always perform one or more validation steps to make sure that this is actually a reliable network. The one I will be using here is what we call the data perturbation. That is basically what it does. It learns the same network under noisier conditions, or rather it uses the same learning algorithm with artificially generated noise. This way we're trying to make sure that we're not stuck on a local minimum just because of the precise sample we have. So let me just,
Are you able to save networks almost like you would save a starting seed in a segmentation or a cluster analysis? Are you able to save network runs in case, let's say, you adjust it and then you decide, well, I actually like the other one?
oh, absolutely, absolutely. So you can save networks and also formally compare them, like by overlaying them and then comparing, okay, what is different between the different networks. Yes?
What is the minimum spanning tree? What is the maximum spanning tree?
That's, I actually have never heard of a minimum spanning tree. We're only using the maximum weight spanning tree. But that is actually not a proprietary algorithm that we have, but that's, and now I'm not a computer scientist, but if you Google maximum weight spanning tree, you'll find that as a search algorithm. Adnan, I think you had a question.
Yeah, okay, I'm sorry. Just to continue the question about comparing the algorithms and the network, visually comparing or comparing some numerical or
Both.
numbers or
Both.
some kind of distance, magnitude, or how?
Yes, here you could actually compare both. You can compare the score, the minimum description length score of the networks, as well as the actual how different the structures are, with a visual differentiation between the
What I'm
net.
looking for is the actual significant movement.
Mhm.
So is there some kind of values that you say, okay, there's a risk, what I'm looking for, risk zone or some, how?
Yes.
the
Yeah,
risk
absolutely.
is to move from one network to another
Yes.
network.
And a good way to approach this is here, for instance, with what we call the arc cross-validation. So we relearn the network multiple times using different subsets of the data, and then compare the structure. Then we see which arc was found every time, regardless of the subset. And there may be some arcs that we only found for some instances of the subsets. And given the arcs that we find every single time, we then have a high degree of confidence that there is a real relationship. Then if one arc is only found, in 1 out of the 10 iterations, then we can say, that was just like a spurious find, but we should probably not include that in the final model. So there are a number of steps like this that we can and should take. I will omit that for today, simply because it would take quite a bit of time. But in the book, in the context of the perfume example, you will find that illustrated in more detail. Yeah? So I will only do what we call the data perturbation. And what you can, whoops, it was so quick I couldn't even see it. Here we now have at the bottom now a new score, or rather BayesiaLab has manually introduced artificial noise into the data set and then relearned the network. But what we see here now, despite that noise, we couldn't really find a lower score than what we had originally found. So now we can be pretty sure that the network as we have it is actually a reliable network. Yeah?
This is learned only once or many times?
In this case, it was actually learned several times with different levels of noise. Yeah.
There was like a 10, you filled in how many iterations it would run, right?
Yes. Exactly.
Where is the scope? Is in the console?
In the console. You can always have that open up the console, and as you learn, you will kind of get a sequence of values. Kind of for each iteration, you'll get a new score.
The console will always show the best network score.
Yes, but you can also kind of scroll back and then see, each iteration of the learning. I'm scrolling up now. You see all the different learning steps that took place with the corresponding minimum description length score.
So which iteration am I seeing the best?
Here, in this case, BayesiaLab shows you the best. Yeah.
Best in terms of MDL?
The best in terms of MDL score, yes. Okay, so now that we're reasonably confident that this is a good network, I will now perform clustering on that. And what I should want to illustrate first, though, is how that automatic clustering process will utilize this network. So I will briefly turn on the arc force, and arc force is what we call the Kullback-Leibler divergence, which is a measure that relates to the individual arc. The Kullback-Leibler divergence for an arc tells us the difference in the joint probability distribution of the network with and without that particular arc. So this gives us a sense of how important an individual arc is in the overall network. Now, given that we have a tree, or we learned this with a maximum weight spanning tree, and this network is a tree, the arc force is in fact identical with the mutual information. So, but regardless of the precise definition of this measure, let me just illustrate here and visualize. What I will do now is I will play here with our slider, and actually, while you're back there, could you perhaps close one of the blinds, because I think the light is now coming in directly from the back. Also one over to the right, perhaps. Then perhaps we'll be able to see the screen a little better. Thank you. I think that's great. So I've just raised the threshold for viewing the arc force. And by moving that slider all the way to the right, we now only see the single strongest arc in our network. Let me zoom in here. And what we have here is sound system controls and ability to control sound quality. Now, it seems like these are very, very close in meaning. And here in this case, that has the strongest of all the arcs that we have in our network. They represent, or these two nodes have the most information in common between all nodes in our network, which makes these two nodes the starting point for a clustering. So as BayesiaLab looks at this, it would say, okay, let's start with these two nodes and merge them into one cluster node, into one factor. And then, I'm just zooming out again, I'm now looking for the next pair of nodes. Now, the next strongest relationship would be these two. I think this is turn signal function and tail light function. And here comes number 3. Appearance of tires and appearance of wheels and rims, and so on. So I'm clicking my way through, and BayesiaLab just keeps looking at what is the next pair of nodes that would have the strongest relationship with each other. And it introduces a temporary factor for each pair. And now, going a step further, now we have another variable that links to a pair of nodes for which BayesiaLab has introduced a temporary factor. So now this group becomes a new factor, and so on. So as we
A new factor, or it updates?
it basically now a factor is created from these 3.
Yeah.
So there was a factor between these 2, and there was a strong relationship between this node, which is body workmanship, and these 2, which is fit of doors, fit of other body panels.
You've
So-
replaced that factor with.
These 2 were initially replaced with a factor, and now this new one is closely related to this existing temporary factor, and so now those 3 become a factor, and so on. So I can now continue this, and obviously it would be very tedious to perform this manually now. So BayesiaLab has this entirely automated through its variable clustering function, which I just turned on. And so now all our nodes are highlighted in colors to show their proposed cluster membership. I'll just make it a little bit larger. We can now view what is initially proposed. And here in the upper right-hand corner is the current number of clusters that is proposed. And again, with the slider, I can determine whether I want more or less clusters. You know, whether, and this is really, to a large extent, based on my choice. What is my objective? You know, what is the number of clusters in terms of how I can operationalize this? So, but really a good view to judge the clustering is by looking here at the dendrogram. Now I'll perhaps make this a little bit larger. So this is, oops, let me just. So here you see some of the variables that are clustered together, and you can also see how kind of these clusters ladder up. So here we've had taillights function and turn signal function. They were the initial merge, and then later on headlights function joined that cluster. And then as a next level, braking joined this existing cluster. And so on. So here we see the initial proposed clustering, but that is by no means final. You know, I can determine, I'm now moving that slider here on the upper right-hand corner, and that shows me of the different possibilities for clustering. So in this, yes?
Yeah, and based on like any given clustering you've selected there, do you get some kind of summary statistic for how it would describe the...
Well, here not at this point. I don't get a summary statistic for any of these. I will later on when I perform when I basically implement the clustering. I will get measures as to how well the factors represent the manifest variables.
So when you're choosing the number of clusters, you do it more or less visually. I'm trying to draw parallels to PCA where you get like a scree plot or something
Yes,
of the sort, right?
exactly. And see here basically you need to determine, well, does this make sense? Here, appearance of tires, appearance of wheels and rims, should that be one entirely separate factor, or should it be merged with the factor that consists of door handles, exterior trim molding, badging? And it's entirely, you know, your guess is as good as mine. You know, what you need to, stakeholders need to determine, should we lump that together, or are these distinct concepts that, like the end users of this research, they need to keep apart? All right, yeah.
Any indication of the comparison of this to the linear factor analysis? When I take the same data and run it through any of the many algorithms in the factor analysis, I do not get results that are similar. Different in terms of the number of factors, even the composition of factors.
Yes. What is typically very difficult with a traditional factor analysis, it's easy to get like the first 2 or 3 or 4 dimensions, but what is immediately difficult is to identify the meaning, because then you have to do all your rotation and I've actually tried to do a traditional factor analysis on this particular data set just out of curiosity, because I hadn't done a traditional factor analysis in a while. And what I found to be just so challenging through multiple rotations and figuring out, well, what does an individual factor actually mean, and so on. Whereas here, I can say, okay, you know, you visually look at this and you know what it means. And therefore, I find this so much more intuitive and faster compared to a traditional approach.
So
Yeah.
basically, I'm just summarizing so there's a long-term and short-term solutions. So long-term for the new product, new prototype development. Short-term would be kind of what is the most important clusters or variables that we need to improve immediately in order to
Yeah.
going back to screen loss or
Yeah, I mean, here you may have actually different audiences
Right.
in your organization.
yeah.
You may look at this and aim to
Yeah.
inform engineers, and they may want to look at these different attributes actually in more detail, as opposed to the marketing communications team. You know, in marketing, at most you can have like 2 or 3 themes or concepts that you can communicate to consumers. Whereas engineers, if you just give them 2 or 3 themes, that doesn't really help them in their decision making. Because they need to know, well, is it really this feature or that feature? They can't deal with generalities. So let me just quickly illustrate this mapping function, which is a virtually identical representation as the dendrogram, but sometimes it's more intuitive. I can, as I'm changing here the number of clusters, you know, my newly formed clusters are represented here as these bubbles in the mapping plot on the right-hand side. And you can just get a feel for, well, does this make sense? Or, you know, should I differentiate this into further detail? Yes, Eugene.
One thing, so, but the interesting thing here is that we've clustered it, although unlike in factor analysis, we haven't actually lost any information yet, which is why you're saying there's no score to assign to this.
Yeah.
All we've done is group.
We've just grouped it, yes.
Okay.
But once these factors are introduced, we will lose information,
Okay. So then
and
we
which
can
we need
start.
to assess
Okay.
then. Here at this point, it's just like, okay, this is our current working assumption. And to make these current assumptions more readily interpretable, the temporary factors always carry the name of the single strongest node in the factor. So this is not just like, this is factor 27, but rather this factor here, the strongest node is handling, and these are all the other nodes that are currently clustered into this factor. Yes?
What is
Awesome.
the number between these spheres? Is that the
Here in this case, I'm just have to think here for a moment. In this case, it's the arc force.
Okay.
Yeah. So, yes,
Do you have
Alex.
the ability to manually adjust the items within a particular
Absolutely.
factor?
Yes, absolutely.
Because with these types of modeling approaches, a lot of that space validity is a very important thing, because people,
Absolutely.
breaking is better fit safety features.
Absolutely, absolutely. So what I will do here, in fact, is I will choose one clustering, and once we carry that through, we will realize that there are actually 2 examples where the manifest variables actually don't belong into a certain cluster. Yeah. So I will.
The size of the bubbles is the number of subclusters? Or
Here in this case, it represents the node force. And the node force is the sum of the arc forces. Now, and it would probably take up too much time now to go further into node force and the different types of node forces with outgoing and incoming node force and so on. Here, principally, the objective is to have a quick visual that conveys, okay, this is what we have, this is the meaning.
Would it be akin to total effects in a partially squared regression model, or is it not?
Not yet, because here we don't have a target node yet.
Okay.
So it's just like the nodes by themselves. But we will get to total effects because ultimately we want to know, well, what is the importance of an individual factor with regard to the target node. So after playing with this network for a while, I have arrived at, I'm just going with the original proposal. BayesiaLab suggested 31 clusters, and I'll keep it at that. You may say, are these too many or too few? Again, it entirely depends on your particular application. I'm now assuming perhaps we're working with an engineering audience where I need to have a fairly granular clustering. So I'm essentially now reducing 98 nodes to 31 nodes. So I will confirm that. I'll confirm my choice. And then I get a quick report of how my manifests are assigned to the clusters. Yes, Narayan. No, go ahead.
I've seen in this BayesiaLab factoring, the first few factors always have a large number of manifests. The last few have very few.
Really?
Yeah, I've seen that.
Yeah.
If you go down, the last few will have 2 or maybe 3.
Yeah.
That's my experience, at least with PNG data. Here also.
Yeah.
I would say that's
What is
typically
that?
pretty consistent across your factor analysis as well.
No,
Right?
not
I mean,
really.
typically, unless you
If they're sorted by
do
our
some kind of
plan.
data manipulation, you're going to still end up with more items within the earlier factors versus the later factors.
Yeah. But we can really look at that once we introduce our factors. So far, we've just basically created an assignment between manifest and a factor. Now, as a next step, we will generate these factors and create values for these factors. But before we do that, I think we should have a quick break and then perhaps continue in 5 minutes or so, or 10 minutes.
Thank you for the break.
We need to keep moving. We still have quite a bit to do in the next hour or so. So we've now identified the clusters, or rather we've accepted the proposed set of clusters. Our next step will be to formally introduce them into the network. So with BayesiaLab, we do that in the multiple clustering function. That will, for each defined set of clusters, now create a new factor node and determine the optimal number of states, and then create values for the factor, or determine the state of the factor for each observation in our data set. So I'll perhaps go through some of the specific options in this menu. First, I will define an output directory where, because BayesiaLab will, for each cluster and its corresponding factor node, create a new little Bayesian network. And that will be saved as a network into the file directory that I specify. So I'm determining this here. Then we could either predetermine the number of states the newly created factors will have, or, as I mentioned earlier, I let BayesiaLab automatically choose the optimal number of states for the newly created factors. I'm providing a range between 2 and 5 states. Then furthermore, I can determine whether I want to use the entire sample to perform the clustering, or just choose a subset. Sometimes if we had let's say the entire 200,000 observations in here and I wanted to perform clustering, then I might perhaps start with a subset of the data just for reasons of efficiency. So here, with just 4,000 observations, it doesn't matter, I can use the entire data set. So let me run this. Shouldn't take very long. we'll see a little progress bar here at the bottom. Come on, come on. Almost there.
Push it to the finish line.
Yeah, come on, come on. All right, here we are. So let me bring up the report first before we go into the picture behind it. So this is now our clustering report. It gives me an overview of kind of summary statistics regarding the clusters that we found and their fit. I will initially focus on the individual tables for each factor. Let me look at this one here. This is factor 0, which contains the following nodes: electronic display of information, ease of reading, controls and instruments, placements of controls, instruments, instrument cluster gauges, and sunroof. Now, perhaps it strikes you as a little bit odd to have sunroof in here. And when we look at the mutual information that these manifest variables have with factor 0, we can actually see that the mutual information of sunroof with regard to factor 0 is actually quite a bit lower compared to the rest of the variables that are in that factor. So this might be now a point where you'd say, hey, perhaps it was not such a good idea to have sunroof as part of this cluster, because it's really quite a sort of different concept. So both qualitatively through my judgment and by looking at the mutual information, this may suggest perhaps we should revisit the clustering and do it again with sunroof perhaps standing on its own. So we can now go through this entire list and review the factors. We can look at how well their performance. We can look at the fit, in particular what we call the contingency table fit, to really see how good that clustering, how good the factors, the newly computed factors, represent our underlying manifest variables. So now, obviously, we don't need to spend a lot of time looking at all of these. What I will want to do, though, is pull out one of these 5 factors and look at it in more detail. So I will actually want to look at factor 5. And I will open up the network that corresponds to factor 5. Oh, bear with me 1 second. So I will now open up just bear with me. I will bring up this network. This is factor 5, or the network for factor 5. Oh, this is a little bit too large. So we see that these 4 nodes are part of this cluster. And when I open up my monitor panel, I can now see how actually the states of the manifest variables relate to the states of the factor. It's larger, and perhaps I'll move the factor node to the top. Should I just... So here are manifests with their marginal distributions, and here is our newly generated factor node. Here, just just carrying the name, factor 5. And here, BayesiaLab determined for these 4 manifest nodes, a cluster with 3 individuals with 3 discrete states is the best way to represent the underlying variables. By going through these individual states, I can see kind of how the manifest relate to the factor. And here, essentially, what happens is it looks like the factor summarizes the underlying manifest into kind of low, medium, and high. So if we just watch what happens here with the distributions, so here are all the people who are mostly unsatisfied with the roominess. Here, this is sort of the mid-level satisfaction, and here are all the folks that are actually very happy. Yes, Eugene?
To the right of the green there, you have C3, C1, C2 with some scores.
Yes. So these were the original names of the discrete states that were identified in the clustering, which were subsequently ordered by their values. Because the way, like for instance here, the state C2 has a value of 9.3225. That value is composed as the weighted average of these distributions here.
Those
So-
are three clusters in some space, those are their values, and then they were resorted.
Exactly, because in the original clustering, the clusters were not necessarily found in numerical order. So in the clustering options, I actually said, please create factors with ordered numerical states, and this is what we get here. And what I'll just illustrate briefly, this factor variable now has states for every record in our data set. So I will just review that real quick by going to interactive inference. And now I'm going to scroll through my entire database and looking at each individual response. And I can see how, given each manifest response, a factor state was assigned to the corresponding respondent. So this way we really have created a new variable with values. So, yes?
In this case, if I had 4 out of the 5, or 3 out of the 4 question a respondent is missing on the manifest side, it will still have a score for the factor.
Yes. Yeah. So,
But if I have all the 4 missing, obviously no, right?
well, in which case, I would have a probability distribution for the factor. So, because we need to remember that as how BayesiaLab handles missing values, it would then basically carry that missing value, the missing values into the factor. So it would impute a missing factor value the same way it would impute a missing manifest value. Does it make sense?
How would it impute if all the manifest was missing? It still imputed.
It would, here for instance, this is essentially what we would face if all 4 were missing. So we would have for each manifest that is not observed, we would have this expectation. So this would be the distribution that we would expect for a missing value. Yeah? And corresponding to this distribution, we would have an expected distribution for the factor. Yeah? So these would be our placeholders for the missing values. Yeah? Take a look at the missing values chapter, because I'm just now kind of glossing over this a little bit, because there's actually a lot more to how the missing values are technically handled. Yeah. So, okay, so this is just to illustrate now what these factors actually represent. Let me now go back to this busy picture. This is obviously as is, not so easy to read. So I'll apply the automatic layout. Let me turn off some of the labels and perhaps stretch these apart. Now we can see all our manifest variables all circle around the factor nodes that are at the center. So now our next step is to figure out how these factors relate to our target node. Now, there are several ways how we could approach this, and one would be we could now apply a new learning algorithm that discovers relationships of the factor and the target node. So the taboo learning would be one option. I will actually take a slightly different approach. I will now create more or less manually a naive structure that connects my target node, overall new vehicle experience, to all the factors, because I really want to know the importance of every single factor and kind of its weight with regard to the overall new vehicle experience. So I don't just want like the top 5, but I really want to be able to differentiate between all of them. So I will, first of all, bring my overall new vehicle experience back as a node. And now I will connect this, what is my new target node, I will connect this to all factors. So I'll just tell BayesiaLab, please connect my target node to all factors. And now this looks very messy again. A good way of representing this is to do a radial layout, actually. So
what you did, is that a learning algorithm, or you just...
I just said connect.
Everything.
Connect my target node to every factor.
It's almost like a factor regression.
Yeah, exactly. Yeah? And you could argue, well, we should actually do a learning as opposed to just creating a naive structure here. And there are many pros and cons that you might want to consider. For our purposes here, I think this is actually a practical approach, and will allow us to nicely differentiate between the importance of the factors. So
This is with no interaction terms.
exactly. So that's what we will actually need to address. Yeah, let me just complete this step here. I'll do a quick radial layout. Let me stretch this out here. Okay, so now we have the outer ring, if you will. These are our manifest nodes, and then here in the ring in the center, here are all my factors. But as Eugene just pointed out, this would assume that my factors are independent of each other, which is, would be kind of a naive assumption, because that's probably not the case. They're probably all correlated in some fashion. So what we will do to mitigate this potential problem, we will now apply a learning algorithm to see whether there are any relationships between the factors. Yeah. So I will just gloss over some of the little steps I'm going to take. For instance, I'm now fixing the arcs, because I want to retain the existing structure that we have, and then just learn on top of it. Because most learning algorithms that we have erase everything we have and start from scratch. So we actually want to keep this structure because that's our, from manifest to factor to overall, that's what our objective is. So we only want to make sure that our new learning now is applied on top of this instead of replacing our existing structure. Yes?
Sorry, can you show us how you did that? The
Yes.
connection of all factors to the keynote?
So what I did, I right-clicked on the node,
Target.
yeah, and then I said connect, and then I selected the classes.
Got it. Okay.
So I said connect just to the factors.
Okay.
Yeah.
And the factors are connected to the manifest anyway.
They are already connected. One more thing I did is I actually highlighted all arcs and then said fix to basically lock them, to protect them from our subsequent learning algorithm, because I don't want them to be erased. So I had to do that, and then only the taboo learning algorithm I can actually apply on top. Yeah. So that I will now learn on top of this existing structure. And you can see how it learns. And you can also keep track here of the score, as the network is re-evaluated based on every possible network that could combine or connect our factors. And this is what we ended up with. So here this is now, these are the relationship between our factors. And as you can see, there are quite a lot of them. So they are far from independent.
Did you set any forbidden arcs from among manifest variables?
That is correct, yes. I set that in the options as we were performing multiple clustering. I had the option prohibit connections with the manifest. Because otherwise, if I had not set that option, we would actually find all kinds of additional relationships between the manifest. So I have artificially imposed the constraint that the manifest are only connected to the factors, but that there are no relationships between the manifest. Of course, that's an arbitrary choice that I made. I said, I want to look at my domain in this way, that I now just want to think or consider the dynamics through the factors as opposed to directly from all the manifest. So, but that's part of the overall structural equation modeling approach here. Yes, Narayan.
So what is the additional learning you are getting by keeping the connection from the factors to the manifest? So they are fixed anyway to begin with, right?
Say it again, please.
What is the additional learning you are getting by retaining the factor composition, the factor to manifest in this diagram?
Oh, you mean why do I keep the manifest? It's a fair question. At this point, I could say I just discard them entirely, and I will only work with the factors. But sometimes later on, when we optimize our factors, then I might want to go back, well, what manifest levels would relate to certain factor states? Because now I'm going to optimize on that basis, and then perhaps once I have my results, then I might want to see, okay, what does it mean then for these guys? And then I go downstream again. But indeed, I could now detach the manifest and just work with the factors.
So is this same as, say, other than you fix the arcs before you learn the stuff? Can you, there's a step, I think, when you specify the learning algorithm,
Mhm.
you can say keep the existing structure
Yes.
the same.
Yes. So there are actually two things I need to do in order to keep the arcs. These arcs are automatically fixed through the multiple clustering process. So there was actually an option in multiple clustering that allowed me to fix those, and you can see that that arcs are fixed by the dotted line. If an arc is fixed, it is represented with these with dotted lines as opposed to a solid line. But these arcs that I manually created, they were not fixed. So I manually fixed those too. Once I had all arcs fixed, I could choose taboo learning. And with taboo learning, I still need to select keep structure. So I'm kind of double protecting here. First I fix, and then with taboo learning, I select keep structure. And then I can actually achieve the on-top learning without replacing everything we have. Yeah?
In SEM terminology, you're adding more and more paths.
I'm adding what?
More and more paths
Uh-huh.
to the record.
Yeah. Yes. Yes, in this case, absolutely, yes. So now let's see, what have we actually gained here? I will now, for the moment, just focus on the factors, and I will turn on their labels. We saw these labels before. They reflect, or they show the strongest manifest node within the factor. So instead of looking at factor 0 through 30, we actually have these temporary labels on top of the factor, so they are actually somewhat meaningful. Yeah? One thing I could do is now run a target mean analysis to see how these factors now relate to our overall satisfaction. And now we see here, instead of 100 parallel lines, we see 30 parallel lines. And you may say, well, what did we gain? It still looks like, gee, anything we improve here will improve our overall satisfaction.
So here, for this one, I understand this is beautiful visualization. It's good to show, the fancy stuff to your manager. But when you do the actual prediction of, the actual structure of the knowledge the network represents, we definitely need simple structure other than, this complex flower plot. You say, symmetric flower plot.
Yeah. So what we now want to here, this is obviously just a visualization, and then at this point we may think, what have we gained? Because this doesn't look much more insightful than the original plot with 100 parallel lines. So what we now need to use this for is how can we differentiate and figure out, is there any of these that is truly more important or less important for a particular product? So that's our challenge now.
So, but still, this is still some kind of improvement from the beginning, isolating these variables.
So we now,
they're, highly correlated, and so.
yeah. So we now have we have a variable reduction, and it may be a little bit more intuitive, but we're not anywhere close to our final goal, because we really want to figure out, well, which of these for any given product should I improve? What's the easiest way for us to get greater satisfaction from our customers? Narayan.
Can I imply that all these relationships are more or less linear?
Here in this case, it turns out, well, gee, they are actually all pretty much linear. Yeah. But it just happens here. In the perfume example in the book, you will see many are linear one is nonlinear.
Intensity.
Yep, intensity. Here, it looks like we've just mostly, they're actually not, in a few slides we will see they're actually not entirely linear, but almost.
Yes, because this is, first the fixed structure is a naive base net you first fix. Each of the factor you have a direct connection.
Mhm.
That will contribute more to the target variable mean. That's why I guess,
Yeah.
have the linear stuff over here.
Yes.
The question I'm thinking is, looking at this plot, even after a lot of reduction, the factors still seem to be pretty highly correlated.
Yes, yes, they are. So the question is, well, what did we gain? What have we achieved so far? All this for, going from 100 to now 30 parallel lines. We may look at this here. So this was the original plot, and this is now our just looking at the factors. So what did we gain? Well, let's now look at, or rather, where do we go from here? How can we use this for optimization? So let's stick with the 30 factors for now, and think about what could we now do as optimization. So, and you may wonder, why don't we set all of these factors to the maximum? Why don't we just think, let's hypothesize about our customers to be perfectly happy on all fronts? Yeah? And you may say, well, that would probably not be realistic. My question back to you would be, well, what is realistic? If
we can't set the whole on the maximum, so there's some optimum, right?
Yeah, but
So, because they're related to each other.
yeah. So, but looking at this, in theory, why don't we set everybody
Yeah.
to here? Yeah. So, but if not that, then what is a reasonable step? How far we should push it? So what we need to do is we need to introduce constraints. We need to figure out how far we can stretch that, how far we can simulate something better. And we actually need a couple of constraints. There are actually multiple issues we need to address now as we work our way towards optimization. So let's first talk about the optimization constraint number one, if you will.
That's a quick question.
Yes.
So let's say that in food and beverage industry or consumer packaging products, we use different softwares. Some softwares are good for, to developing PLS or some. Is it possible just take the data from this step, and say, good enough, so can I just apply this data to jump or different software that I can do the optimization, and so?
Yes and no. Actually, the optimization you absolutely want to do in BayesiaLab, because as we will see, we need to know the joint probability distribution.
Okay.
So that's a core element. And let
So
me
it's recommended to continue.
absolutely,
Yeah, okay.
absolutely. Otherwise, you would lose most of the benefit of the Bayesian network. So let me illustrate it. So if we had we not developed a Bayesian network, and had we just done a regression, and if we were just to look at a single variable, let this one appear to be a really important variable. Length of time vehicle will remain solid, durable. This is on the x-axis, on the y-axis, overall new vehicle experience. We just did a regression between those two variables. This would be our regression line. Yeah? And we could also compute the mean for this variable, the mean for the y variable. And now we could simulate different values, different x values, and determine what the corresponding y value is. I've created an animation for that.
Yeah.
So we're now going up values of x and getting new values for y at each step. And I could simulate the value x equals 100 or 1,000, because this regression line continues ad infinitum. Yeah? But of course, that may be a bit misleading, because let's take a look at this. Because the underlying distribution of the data is different. So even though we have our regression line here, but once we look at the regression line itself, how many data points are underneath is, we don't no longer have. But here, this is the actual joint distribution. It shows here, for instance, there are exactly 6 people who have rated length of time vehicle will remain solid durable at 1.5, who have also rated overall new vehicle experience at 1.5. So lots of observations here, fairly limited observations there. So then as we simulate x values, if we were to simulate a state down here, that would be very unlikely given the distribution of the data, as opposed to simulate something here. Yeah? So it's not just picking any old x value. It is some of them are much more probable than others. Here I'm just looking at the actual data points behind this bubble plot. And we see here, actually, this is the most frequent observation, where people rated this 7.5 and that's 7.5. And if I were now to simulate a hypothetical scenario, let's say we simulate people like it at rate this at 9.5, I'm essentially conditioning on 9.5. So I'm losing roughly 75% of my underlying observations. So a simulation of a hypothetical scenario is like conditioning on a certain value. Now the question is this realistic? If I just now make up x equals 9.5, is this realistic? Here is just a slightly different representation. This is my marginal distribution. This is my new hypothetical distribution, where I say length of time vehicle will remain solid durable equals 9.5. What we're now taking into account is the joint probability, because this reflects how many observations that I've actually observed correspond to this hypothetical distribution. So actually 26% of all my respondents are actually already in this bin. So I will now use the joint probability distribution as a measure how far removed I am from current reality. So this is reality. This is my marginal distribution for these two variables. Now here is a hypothetical scenario, and given that I set that to 9.5, my joint probability goes down to 26%. So let me show you where I'm going with this. I'm now plotting the response curve from our model, from our network, the nice, beautiful, flowery chart, or a network rather. And I'm just plotting length of time vehicle will remain solid durable and overall new vehicle experience. So this is my response curve. And it's almost linear, as Narayan said. It's not quite, but almost linear. But what I'm plotting on top here is now the joint probability. If I'm now simulating any value for this variable. So the higher up I go, the smaller becomes our joint probability. And what I will do as a next step is I'm computing the gain, basically the increase of my response curve over the marginal value, which is this red curve. This is now shows me how any hypothetical scenario increases beyond my marginal satisfaction. And I'm now multiplying that, what I call gain, I'm multiplying that with the joint probability at each state. And when I do that, I get this curve. And this shows me that I can't just take everything to the max, because at that point, at this hypothetical level of 9.5, actually my joint probability is becoming smaller and smaller, so that I'm actually worse off than if I had left it at the level of 8.5. So I'm just I'm using the joint probability kind of as a implicit reality check. So I'm not overextending into wildly surreal territory.
You optimize.
I'm optimizing, but here I'm creating I'm using the joint probability to obtain a constraint that I otherwise don't have. Because if I were to simulate your liking of BayesiaLab, why not 10 out of 10? Why only 9? Why not more? And by introducing joint probability, I now can have sort of kind of a natural balance. It tells me how far I'm stretching from current reality. Did you have a question, Eugene?
So is the next step then that since you can do this one variable at a time and you have encoded in your graphical structure all of the joint distributions, that you can do it all at once and do
Yes.
this kind of likelihood?
Exactly.
Wow.
So as I'm basically trying out all different hypothetical scenarios, for each of these scenarios, for each of these simultaneous conditions, I can compute the joint probability. And therefore, I'm kind of weighing, what do I gain? How realistic or unrealistic is it?
Can you go back one slide? So the joint probability, how do you calculate that? Why is the curve like that? Because my understanding is like for each of the, say this one, length of time vehicle will remain solid. You slice the data on different ratings and then.
Mm-hmm. Well, I'm actually directly using the Bayesian network for that. So here I'm just pulling out two variables.
Something we're seeing on the screen.
So, oops, perhaps I should show. So here I have just picked one factor out of these, and if I just look at the marginal distribution, up here I see the joint probability is 100%. Yeah? Now if I simulate a specific value, let's say I set factor 19 to the highest value, my joint probability goes down. So for each set of evidence or combination of evidence, I can compute the joint probability that corresponds to that observation. So for each scenario I'm trying out, I get basically how likely or unlikely that scenario is given the network.
Yeah, I got this. And then the curve you show is like a declining curve,
Mhm.
like a monotonic
Yes.
declining curve. Is that like a specific case for your data, or it will be?
So in that case, it was just a specific case.
Okay,
The
could be
curve,
some other curve.
the curve could really be. I'm just trying to think of the shapes the curve would have, but this was actually derived from this very model.
Okay.
Yeah.
So it could be, like some different, like quadratic curve.
It could perhaps be that too. Yeah. Yeah.
So in that case, you do want to maximize the rating.
In that case, it would encourage you to pursue higher ratings if that's much more likely.
Okay.
Yeah.
So I'm just thinking, so there is a chance that we can create ideal versus realistic.
We want to basically have a realistic maximum.
A realistic maximum, that will be optimum, right?
Yes.
Okay, but is there anything beyond that, like ideal, that is not realistic, but it will be ideal?
Yes, it would be. If everything is just a max, that would be the theoretically ideal, even though it would be not meaningful. Like everybody, because you might get down to a joint probability that represents a single customer. What the scenario you simulate is so unlikely that you may not even have one customer who currently matches that extremely positive scenario. So that was our first constraint number one. Now we get to constraint number two, and that is, well, perhaps we should ask the experts. How far do you think we can go with this? How far can we improve this? What is our realistic goal? Or what we will do now is we will also, we can actually derive constraints from competitors, because we can look at, well, how does the Toyota perform on this measure? How does the Nissan perform? How does the Hyundai? And then we could perhaps say, let's look at where our product stands compared to the best for each of the factors. And then say, well, perhaps as we simulate hypothetical scenarios, we should stay within the constraints and perhaps not exceed the best one, the benchmark, for a particular factor. But it's a choice. It's one of the constraints we could derive. Of course, somebody may say, well, even that would be too much of a stretch for us. So anyways, I'm imposing now a second set of constraints. Let me show you how we derive them. Let me. So here is my network again. Well, we need to realize that this network still applies to the entire market. All models, all the 10 models that exist in this segment. Before we can optimize, we really need to recreate this for every single vehicle model in the market. Because there's no point in optimizing for the entire segment, because vehicles in the segment are different, and we want to perhaps optimize our vehicle as opposed to the market overall. So a very practical tool here is what we call the multi-quadrant analysis. Narayan mentioned it earlier already, I think. We will now recreate this network for each vehicle model. We can do that with what we call the multi-quadrant analysis, which allows us to select our breakout variable for that, we use the variable that represents the vehicle model. And then we have the option of either relearning this model in terms of relearning the structure, or what I will choose, I just will re-estimate the conditional probability tables. Because as we go down into each vehicle, our number of observations becomes smaller. We get fewer and fewer observations. So what I will prefer is I will just perform parameter estimation instead of rerunning the network learning algorithms again. And I will choose an output directory that will then allow us to retrieve these newly generated networks.
So the assumption here is that the factor structure remains the same across all.
Yes. Yeah, that is an assumption. That is an assumption which may or may not hold. I'm saying we've learned the factor structure at the segment level, and we retain this as we go down into the individual vehicle models. Okay? So let me run this now. Shouldn't take very long. Okay. Here I'm getting now my multi-quadrant analysis report or plot. It looks initially a little bit busy. Let me zoom in. Actually, I will just make this a little bit larger. So, this is now similar to the plot I showed you earlier with the individual manifest variables where we had like the fuel economy and the spare tire and all those plotted. Now we have the same, but now just for the factors. So, and this picture initially is just for the overall segment. But now if I hover over my factor, now I get the position of each of the models for, for each of the factors. So I can now see that in terms of length of vehicle will remain solid, durable. The Toyota actually, for Toyota it's most important, but the Mazda 6 is rated the highest. Or here, it's also quite important for the Hyundai, but it is also rated somewhat lower, and so on. So I can now, for each factor, I can see where exactly the models stand.
So the original location is for the entire sample.
So this is for all. So this is on average shows me how all mid-sized segment customers rate their satisfaction and how important it is. By hovering over it, I can see how that breaks down into the individual models. Now, what is quite helpful is to turn on what we call the horizontal scales, because this just gives me what is, the competitive range. So, and this is now interesting because I can now bring up any particular vehicle, and I'll just, for the sake of argument, use the Hyundai Sonata, a vehicle that has beautifully improved over the last few vehicle generations. So what we are now looking at is actually what was the status as of 8 years ago or so. That vehicle has really become much, much more attractive in the meantime. But anyway, so for the Hyundai Sonata as of model year 2009, this is the rating for the variable, and we can see there's quite a gap to the best level in the market. And we can also showcase the vertical scales, which shows us the range of the importance. So we can now take into account, well, how well do we do? How important is it? And what is our gap to the best level? Those are now the constraints we can utilize for the optimization.
Yeah, in the Bayesian network or BayesiaLab context, this interval is what? What is it? Is it a probability interval?
No, here this is the range. This is the rating with regard to the factor.
Oh, okay.
So
Just the range in the data.
this is just the data, yes? And so this gives me a sense, or would suggest,
The whole data of all categories, the raw, medium, and high, right?
yes.
Okay.
This is the rating, the computed rating of the factor.
Okay.
Yeah?
The next question, is there any slider that you can do?
Yes. So what we want to do now is, because we've now for our vehicle, we have like all these relative constraints. Like for each variable, I have the gap from best to worst, and I want to use the gap to best level as a natural constraint. So as I'm optimizing, here in this case, let's assume we are optimizing the Hyundai Sonata. I want to set this as an optimization constraint, because this is the best vehicle in the segment right now. That's the top rating. It's perhaps like 8.1 or so. I'm saying as I'm simulating hypothetical scenarios for the Hyundai Sonata, we probably should not exceed the level of the best vehicle in the class. So, and I now want to identify, I want to save the gaps to the best level for each factor, and save that as my constraint. We have this little function here that says export mean value ranges, so I can later on retrieve that gap to best level for my optimization. Yeah? So I'll save that now, and let me save into the correct directory. It's just a little text file that I can later recall for the optimization. So, all right. Now I can turn to the vehicle I want to optimize. Because BayesiaLab has now created 10 networks, one for each vehicle model. And I will now randomly pick one, or I will not randomly, I'll just pick the Hyundai Sonata, and that we want to optimize. So here are my 10 individual networks, one for each vehicle model. You can see here's the vehicle model attached to the file name, and I will open the network for the Hyundai Sonata. So now this looks identical to the network before, but this has been re-estimated based on the observations just for the Hyundai Sonata. Yes, Eugene?
And you mentioned it was re-estimated, not refitted, so is it just kind of like, I'm trying to understand, you basically go in and just limit the data set to those
Yes.
rows, and then whatever distributions come out of that is?
Correct.
Okay.
Yeah. So the conditional probability tables in this network have been re-estimated based just on the Hyundai Sonata survey responses. No? So, and this now serves as the basis for optimization. This is I will now want to optimize these factors, and in such a way, on the one hand, that I'm staying within the constraints, but then also I want to remain realistic. I don't want to stretch too far from my current reality. And briefly need to go back into PowerPoint, because I need to share with you how we actually have to simulate variables. There's another degree of complexity here. So let's assume we have this node. Length of time vehicle will remain solid. This is my marginal distribution. Of all survey responses, this is the marginal distribution, which has a mean of 7.706. So if we now said, okay, let's simulate something higher than that. Let's simulate a value of 8. There are actually a number of ways how we could simulate that value. The first way to do it would be to do a binary simulation. This would be what I'm showing here. I could create a distribution that consists of 75% state 7.5 and 25% state 9.5. That distribution would create a mean value of 8. Now, one could say, well, this isn't very realistic, is it? You know, to go from this distribution to that distribution, because we basically say there is absolutely nobody in the bottom 3 bins. You're right, not very realistic. An alternative simulation would be what we call value shift. And that is equivalent to moving every single respondent by exactly the same amount. Basically lifting everybody's response by the same amount. And this way we arrive at this new distribution, which once again has an expected value, a mean value of 8. A third way is what we call simulation by minimizing the cross entropy. And that is taking this original distribution and searching for the distribution that is as close as possible to the original distribution, but in such a way that I achieve the new value of 8. So these are the 3 ways I could generate a value of 8. Actually, there's an infinite way of how I could simulate the value of 8. But these are the 3 ways we can simulate it with BayesiaLab. Now, which one is the most realistic? I'm arguing that it's actually this one here, because this is the closest to the original distribution. So this is the one where I'm least departing from my marginal distribution. So this is what I will use to simulate whenever, as I'm searching up and down the scale of values, this is how I will, for each value that I'm trying to simulate, I'm looking for a distribution that achieves that value through minimizing the cross entropy. Yeah? Now you may wonder, well, why do we have these other approaches available? Well, if we were to look for if we were to optimizing marketing mix, in that case, I'm actually looking for single point estimates. I'm looking for what is the precise number of dollars or this precise amount of dollars I want to spend in each channel, in each marketing channel. In that case, I'm looking for a dollar amount as opposed to a distribution. So in that case, I would use the binary simulation that gives me an exact value. There, I'm saying I'm dialing in my exact value that I want to spend on each channel, as opposed to here, I'm simulating hypothetical distributions for consumers. Yeah? So that's the simulation part. And there is another consideration that we need to bear in mind, and that is how exactly we optimize. So this is the type of optimization we wish to perform. In BayesiaLab, we actually have 2 principal optimization approaches. One is a genetic optimization, and this is what we would use for marketing mix optimization. Because there, I have all my marketing channels, and I'm trying to kind of fine tune exactly what I should spend on every single one. I have control over every single channel in my marketing mix. As opposed to, for my key drivers, I rather want to identify priorities that I can bring about among my consumers, or I will identify areas where I can lift my consumers' perception. So I could theoretically do this for my consumer perception. I could say, well, if I could theoretically create this precise mix of perceptions in my consumers, then I would get the overall optimal satisfaction. And it would be great if I could adjust my consumers in that way, if I could precisely dial in everybody's opinion to a specific level. But that's not actionable. I hate that word, but here I think it is appropriate because I cannot precisely create your exact belief about my product. If I were to manipulate marketing spend, there I can precisely set what I want to spend. I think brand perception of a consumer is more like trying to steer an oil tanker. It's very, very difficult to turn it around. It has an enormous amount of inertia, and it will be difficult just to change its direction in one dimension as opposed to trying to, precisely aim it. So the optimization that we're trying to pursue is kind of what's the low-hanging fruit? What's the first step we should do? If there is anything that would enhance our consumers' overall impression of our brand, what's the first thing we should address? So let's do that. And then after that, what's the next thing? So we then perhaps end up with the top 3 or top 5 priorities for our product that our engineers should address or that our marketing communications team should focus on. So that's a very different optimization from what we might use for a marketing mix optimization. So this is the one we're going to use. Yeah?
So the priority one, where is it linked to the factor 1, factor 2, or how?
Yeah, that's the one we want to find out. We want to find out which one is it. What's the first thing we should do regarding our product? If we fix that, that would greatly improve if we improve that one detail rating or the rating of the factor, that would most improve our overall satisfaction of the consumer. That's what we find out. This is, interestingly, exactly the approach our hotel clients take, because they get all these surveys from the hotel guests. And there the question is, well, what's the first thing we should do? Is it cleanliness? Is it F&B? Is it recreation facilities? Is it outdoor? What is it that would most improve the overall satisfaction with the stay? So let's now do this. I will now switch back into PowerPoint. We have selected the Hyundai Sonata, and I can access the optimization.
It's not showing you.
Oh, thank you. I need to close out the presentation first. So here we go. So here we have the network for the Hyundai Sonata. I will now go into the optimization menu and select dynamic profile. So this now gives me all the options that I have. And now this is a very generic optimization approach. So there may be some domains where I want to minimize or maximize a certain state and so on. Here, I want to optimize the mean. I mean, I want to actually maximize it. And I want to take into account the joint probability. So I want to use this implicit constraint that kind of is my automatic reality check. I want to simulate mean values, and here I select minimum cross entropy. So as opposed to the other ones where I showed you the slide earlier. And just in edit variations, I now have the ability to either specify expert set constraints for optimization, that I just say, you know, on this topic we can at most increase by 5% and so on, or I will use the file that I saved earlier with the gaps to best level. So I'm now retrieving, and we see on factor 0, for instance, Hyundai could improve by 7.7% before it reaches the best on factor 1, and so on. So for each factor, I've now retrieved a constraint. But perhaps some engineer may look at this and say, hey, you know, this is really, we can't aim so high, we can't catch up with Toyota or something, so I can now set an alternative constraint. You know? If we had cost available, I could also introduce that here. Because on certain measures, I may have from experience from other vehicle models, I may say, you know, this has cost us so much in investment to bring about this change in the past, so I could now associate costs here too. And depending how technical the measure is, that is more or less realistic. For instance, rating on fuel efficiency. So here, in this case, it is reasonable to assume that the rating on fuel efficiency is very close to fuel consumption. So there you may have a value that, you know, I improve fuel economy by so much, and then I have a corresponding improvement in the rating. And for the fuel efficiency, I have perhaps a cost to my company to bring about a certain improvement. You know, a 5% improvement in fuel economy may be a $100 million investment or something like that. So if I had such values, I could introduce them here. But we don't, so we'll proceed without. And I will say, bring back to me the top 5 scenarios, or the top 5 priorities rather, that would give me the biggest bang for my effort. Let me run this. So here we see our little report.
If you did all 31, you simply have a recorder of all the items.
Yeah, I will, here in this case, I will just want to retrieve the top 5 items, and I want to see if I were to implement them, what would I get? Okay, here we are. So here's the report. Let's make this a little bit larger. So this now tells us that these are the top 5 things we should improve for the Hyundai Sonata. So what is this? Factor 0. This is the factor that relates to electronic display of information, gauges, instrument cluster. And given that vehicle, it is not surprising that that is the first thing to improve, because in this particular vehicle, for this model year, the instrument cluster was fairly basic, so this seems to be a rather obvious result. This now suggests if we can increase the rating for factor 0 from 7.7 to 8.28, then the overall rating, the overall satisfaction will increase from 7.7 to 8.02. So this is basically the top priority for this particular product. And then, if we were to implement this, then the next step would be factor 28. That's the next thing we should work on, which apparently is related to performance. So, here in this case, now what we need to bear in mind is that these factors are not independent. So everything is associated. Everything is associated in the consumer's minds too. So as we're improving one factor, you can't just improve one factor in isolation because everything is correlated in the consumer's mind. Here, we would realize that by improving factor 0, we would have in fact lifted factor 28 implicitly. So in that case, our remaining task for lifting factor 28 is just a step from 7.52 to 7.98. That would bring an increase in the overall satisfaction from 8.02 to 8.1 roughly, and so on. So I can now see that as I go down my list of priorities, the further improvement declines. So my first lift was like 0.3 or 0.32, and then my further possibilities for increase go down. So, but this is now really the list of priorities I can take back to engineering and say, okay, here, these are the tasks we have for our product. This is where we should focus our energy. And this is really how product development works from my experience. As you venture to develop, to define a new car, you set targets. You say, okay, these are for the next generation of this product. These are the things we need to improve or need to change. And this is a tremendous help for product development in identifying, well, what is it? With all the things that appear to be so closely related. Remember, a few minutes ago, we were just looking at 30 parallel lines where it all suggested more is better. But now we have a much more differentiated view of this, where we have 5 clearly distinguishable factors with a very, very clear priority as to what we should do. So this is what you take into the board of directors meeting. But of course, then somebody will say, oh, you know, we can't do this for regulatory reasons. We can't do that for cost reasons. So then you can go back, set new constraints, and run the optimization again. So it is an iterative process, and BayesiaLab makes these iterations very, very easy to go through. You know? Or you get a new wave of the survey, you know, you get the data for the next quarter. You can then re-estimate this network with new data and optimize on this basis again. So in that sense, actually, our work with Procter & Gamble has been tremendously helpful in developing this workflow. And so actually now many organizations around the world are using this particular approach to optimizing their products, their campaigns, etc. So, Eugene.
You mentioned about the iterative and reproducible nature of it, like if someone wants to rerun some part of it or like rerun the entire analysis from scratch, is there some script that gets saved in the background that can generate this whole thing given the data set? Or
Yeah, there's no script that would automatically regenerate it, but you can save what you have in your console, which tells you what exactly you did.
Right. So it would be like a step-by-step process for a
It would-
new user, like for teaching a new teammate, for example.
Yes,
Okay.
yes. So, now let me switch back into PowerPoint one last time, because now you have the opportunity to try out all this. Many of you have already the full BayesiaLab software. For those who don't, we have trial versions available. And I should mention that there are two trial versions. One is the trial version for the general public, which is quite limited in terms of the observations and the number of variables. We'll gladly make a full trial version available to you. Just send me an email and say, hey, I participated in the seminar. Can I have the full trial? And we'll gladly make that available. You will actually need the full trial for replicating the example in the book in chapter 8. So with the limited trial, you won't have enough capacity. I've already mentioned the book. You will receive by the end of today or tomorrow, you'll receive your badge via Credly. Once again, I'd like to encourage you to join us for one of our courses. So again, Nick is the expert. He's gone through all of them, so he can speak with authority about the courses and what they're like. I would also like to encourage you to take a look at our website for videos from our most recent conference. Actually, we have posted videos from our previous conferences as well. For instance, we had Judea Pearl as a keynote speaker at our conference in LA. He gave a great talk. He was supposed to speak for 45 minutes. He spoke for over 2.5 hours, but it was really cool. So take a look at the website for lectures from different clients and Bayesian network researchers. And I would also like you to consider our conference in Paris later this year. This will be the first time we're hosting the BayesiaLab conference outside of the US. Great excuse to travel to Paris. Start on your travel application process now. Perhaps you'll get it approved in time for the conference. Would be great to have you. So, I'm way beyond the originally allocated time. You've had great questions, and we can certainly continue afterward offline, or you can email me any questions. But is there anything perhaps that I could address now, Narayan?
Yes. A question that I've been pondering for a long time. I use this a lot. I sell this heavily to my clients. And I always wondered, is there any watch-outs?
Mm-hmm.
Next thing to slice bread, I really agree. Anything from your experience that I should tell my friends, oh, by the way, in this situation, this may not be right.
Yeah, I mean, there are clearly certain pitfalls, and in the workflow that we propose, we're trying to highlight those pitfalls. And as it relates to learning, for instance, we need to watch out for finding a local minimum. For that reason, we do things like data perturbation, arc cross-validation, so we're not making a mistake there. Discretization has been a challenge in the past in terms of which is the best discretization algorithm. That has become easier now with the R-squared genetic optimization discretization algorithm. Now today we didn't talk about discretization at all, but that in general is an important topic. So that's a pitfall where you can go wrong potentially. And then the errors that you make first with discretization and then with if you potentially learn the wrong network or suboptimal network, that then carries on and kind of burdens the rest of your analysis. Kind of if you have the wrong model, then everything downstream will be affected. So those are the things where, but the best way to overcome these challenges is, sticking to sort of the recommended process, to going through the cross-validation, etc. I think in with some of the new functionalities in BayesiaLab, that has become easier. Because there are now a few more functions like the R-squared genetic optimization, where there is a kind of an autopilot approach. I mean, you should never really use this software on autopilot, but there are now more default choices that put you on a relatively safe path.
Going back to your comment about discretization, is that a must if I have 5 points?
No, then you don't. Then you don't. If you have a 0 to 100 scale or something, or a sensor measurement, a purely numerical variable, then you need discretization. But if you have already like five boxes for the consumer's response, then you can just leave it at that. But with all these things, please just reach out to us with practical questions, hypothetical questions, any problems you may encounter or business problems you currently have that you'd like to solve with BayesiaLab or with Bayesian networks. Just communicate with us, reach out to me via email. If I can't answer the question, I'm sure some of my colleagues can. I think one of the advantages you have, we're a relatively small company, so the distance from end user to developer is actually very short. So very often you will get the answer from somebody who has actually developed the code or written the code. And in that sense, we hope we can be responsive to our customers' need. And so that's really, I think, a very important part. And in that sense, I should also thank you, all the organizations, in particular P&G, that has been so instrumental in giving us feedback about the workflows in BayesiaLab. All right, with that, I thank you very much for your interest, for the time you spent with me this afternoon. I really appreciate it, and I hope we can remain in touch. Thank you very much.
Thank you.
Thank you.